Hello there and welcome to our channel, where curiosity gets comfortable and science takes its time finding the softer paths between questions and answers. Tonight, I'd like to invite you to settle into a story that begins at the very edge of the world in a place most of us picture as endless white silent winds and ice that seems older than memory itself. But instead of starting with frost and darkness, let's gently turn the page in the other direction toward warmth, green landscapes, and a version of our planet that feels almost like a forgotten dream tucked away in a very old book. Before we wander too far into that distant past, let me ask you something simple and quietly personal. Where are you listening from right now? Are you wrapped in a blanket on a couch, leaning back in a chair after a long day, or maybe lying in bed with the lights already low? And what time is it in your little corner of the world? Morning, afternoon, or one of those peaceful hours when the day has finally let go and night has taken over? It's a small detail, but somehow it feels fitting to talk about a continent shaped by deep time, while each of us is here in our own precise moment sharing this one. If you find this gentle journey soothing, or if it gives you a quiet sense of wonder about the planet beneath your feet, I'd be grateful if you gave the video a like or subscribe to the channel. It helps this calm space reach other people who might need a soft place to land at the end of their day. And now, with that small bit of housekeeping out of the way, let's begin our slow walk southward. Not just across the map, but across millions of years. When most of us think about Antarctica, we imagine a land that has always been the same. A vast frozen plateau edged by towering ice cliffs and surrounded by restless cold oceans. It feels timeless, almost permanent, as if it has always been this way and always will be. Yet the Earth has a habit of quietly reminding us that very little stays the same for long, especially when long is measured in geological terms. Continents drift, oceans open and close. Climates shift, sometimes gradually, sometimes with surprising speed. Even the most solid parts of our world are, in their own slow way, travelers. So picture for a moment not the Antarctica of today, but a version of it that would feel completely unfamiliar. Imagine standing where the South Pole now sits. But instead of ice crunching under your boots, there is soil, dark, rich, and damp from recent rain. Instead of a horizon made of white and pale blue, there are trees, not towering tropical giants perhaps, but forests nonetheless, stretching across rolling hills and shallow valleys. There are rivers, not frozen channels under kiln of ice, but open flowing water winding their way toward a distant coast. The air is cool, maybe crisp, but not deadly. You can breathe easily. You can hear things. Wind in leaves, water moving over stones, the distant calls of animals that no longer exist. This isn't a fantasy world built from imagination alone. It's a version of Antarctica that science has been slowly uncovering piece by piece from clues buried deep beneath the ice. Because Antarctica, for all its cold and isolation, keeps records not in books or stone tablets, but in layers of rock, grains of pollen, fossilized wood, and chemical signatures locked inside ancient sediments. Each of these is a quiet message from a time when the planet looked very different. To understand how a frozen continent could once have been green, we have to step back and think about how the Earth itself is put together. The ground beneath you, wherever you are right now, is part of something much larger than a single country or land mass. It's part of a moving puzzle made of enormous plates of rock, called tectonic plates that float on the slowly shifting semi-molten layer below. These plates move at about the speed your fingernails grow. That doesn't sound like much, but over millions of years, that tiny motion adds up to entire oceans opening, mountain ranges rising, and continents drifting from one climate zone to another. Antarctica hasn't always been parked at the bottom of the world. There was a time, far back in the planet's history, when it was closer to the equator, nestled among other land masses in a giant supercontinent scientists call Gondwana. This was a world where South America, Africa, India, Australia, and Antarctica were all connected, forming a massive stretch of land that spanned different latitudes and climates. In that arrangement, Antarctica wasn't isolated by cold oceans or locked in a polar position. It was part of a much larger, warmer system. As Gondwana slowly broke apart, the pieces began to drift away from one another. Antarctica, over tens of millions of years, started its long journey south. This movement didn't happen all at once. It was a gradual slide measured in centimeters per year, but the effect was dramatic. As the continent moved closer to the South Pole, the amount of sunlight it received changed. Seasons became more extreme. Winters grew longer and darker. Summers became shorter and cooler. The stage was being set for a very different kind of landscape. But before the ice arrived, there was a long stretch of time when Antarctica lived in a kind of in-between world. It wasn't tropical in the way we might picture rainforest near the equator, but it wasn't frozen either. It supported forests made up of trees that today are found in places like southern South America and Australia. Fossilized remains of these plants have been found in Antarctic rock, including leaves, wood, and even pollen grains so small they can only be seen under a microscope. Each one is like a tiny signature, proof that plants once grew where ice now stands kilometer thick. Some of the most striking discoveries have come from layers of rock that date back to around 90 million years ago during a period known as the Cretaceous. At that time, much of the world was warmer than it is today. There were no permanent ice caps at the poles. Sea levels were higher. Dinosaurs still walked the land. And Antarctica, despite experiencing long months of darkness each year because of its high latitude, supported forests that could survive those conditions. It's a strange idea to wrap your head around. Forest growing in a place that still had polar nights. But warmth makes a big difference. Even with months of darkness, if temperatures stay above freezing and the growing season is long enough, plants can adapt. So, modern trees in places like Alaska and northern Scandinavia do something similar. They grow quickly during the bright summer months, then slow down or stop entirely during the dark winter. The ancient forests of Antarctica likely worked in much the same way. Along with plants, there were animals. Not just tiny insects or simple creatures, but larger, more complex forms of life. Fossils of dinosaurs have been found in Antarctica, including the remains of plant-eating species that would have wandered through those ancient forests. There were also early birds, amphibians, and small mammals, all part of an ecosystem that feels almost impossible to connect with the silent, frozen continent we know today. As you sit and listen, it might help to imagine that world not as a single moment, but as a long, slow film playing over millions of years. Trees growing, dying, and being replaced. Rivers changing course. Coastlines shifting as sea levels rose and fell. Life adapting to subtle changes in temperature and light. Then, gradually, the tone of the film begins to change. One of the most important shifts came when Antarctica finally separated from its last major neighbor, South America. For a long time, the two were connected by a land bridge, which helped block the flow of ocean currents. Warm water from the north could reach the southern regions more easily, keeping the climate relatively mild. When that connection broke, a new ocean passage opened up, allowing a powerful current to form around Antarctica. This current, known today as the Antarctic Circumpolar Current, circles the continent without interruption, acting like a cold moat. That cold, fast-moving ring of water changed everything. It cut Antarctica off from warmer ocean influences, allowing the continent to cool rapidly. Snow that fell in winter no longer fully melted in summer. Year after year, layer after layer, ice began to build up. Glaciers formed, spread, and eventually merged into the massive ice sheets that now define the continent. From the outside, this might seem like a sudden transformation, but in geological terms, it was still a slow process, unfolding over millions of years. Forests retreated. Animals either adapted, migrated, or disappeared. Rivers froze or were buried. The land was reshaped by the steady, grinding movement of ice. Yet, even as Antarctica became the frozen place we recognize today, it didn't completely erase its past. Beneath the ice, the old landscape is still there. Mountains, valleys, riverbeds, and lake basins remain, hidden but intact. In some places, scientists have used radar and seismic surveys to map these features, revealing a continent under the ice that looks in many ways like any other, complete with ranges of peaks and networks of channels carved by flowing water long ago. Every so often, the ice itself offers up more clues. When researchers drill deep into the ice sheets, they pull up long cylindrical cores that contain layers built up year by year going back hundreds of thousands, and sometimes millions of years. These layers trap tiny bubbles of ancient air, dust from distant volcanic eruptions, and chemical traces of past temperatures. By studying them, scientists can reconstruct what the climate was like when those layers formed, building a detailed picture of how and when Antarctica crossed the threshold from green to white. There is something quietly humbling about that. The idea that the air you are breathing right now has ancestors in a sense that were once sealed inside Antarctic ice. That the climate patterns shaping your day are connected through a long chain of cause and effect to shifts that began when continents were still moving into their modern positions. As we move through this story, it's worth remembering that Antarctica's transformation is not just a tale about the past. It's also a mirror held up to the present. The same forces that turned a green continent into a frozen one. Changes in ocean currents, shifts in atmospheric composition, movements of land and water are still at work today. They move more quickly now, influenced by human activity, but they are part of the same system. For now, though, let's stay with the earlier chapters of this long history, in that time when Antarctica was still learning what it would become. Think again of those forests standing under a sky that would go dark for months at a time, then blaze with low circling sunlight in summer. Picture animals adapted to that rhythm, living in a world that balanced between warmth and cold, light and shadow. Consider the slow drift of the land itself, carrying those ecosystems farther and farther south. Like passengers on a very patient ship, there's a quiet continuity in that image. Even in a world that feels stable and solid, everything is in some sense on a journey. The ground beneath your feet is moving. The climate around you is shifting. The planet is turning, circling a star that is itself moving through a galaxy. Antarctica's story is just one particularly dramatic example of that large emotion. As we continue, we can begin to look more closely at the specific traces left behind by that warmer world. The forests that grew there, the rivers that carved the land, and the subtle chemical signatures that still whisper about ancient temperatures and ancient skis. Each of those details adds another layer to the picture, helping us see not just that Antarctica was once green, but what that greenness really meant in terms of daily life on a very different Earth. And as those images start to settle in your mind, you might find yourself gently shifting your perspective. The frozen maps and satellite photos were used to become just the latest frame in a very long sequence. What came before still matters, still shapes what exists now, and still has a way of reaching forward into the present. So while the ice outside your window or in your imagination might feel permanent, it's really part of a much longer, quieter story that hasn't finished being told. There are still layers beneath the surface, both literal and figurative, waiting to be uncovered. And in the slow, patient way of the Earth, those layers continue to shape what comes next, leading us onward into the hidden landscapes and deeper clues that lie just under the frozen skin of the southernmost continent. Somewhere in a quiet room, maybe on a desk, a coffee table, or the glowing surface of a screen, there is a map of the world that feels familiar. Blue oceans, green and brown continents, neat labels tucked into corners of land and sea. It's the kind of image we grow up with, one that tells us without words that the planet is a fixed thing. Africa sits where it always has. South America leans away from it across the Atlantic. Australia drifts off to the southeast alone. And at the bottom, like a frozen signature, Antarctica stretches across the page, wide and white, seemingly content to stay exactly where it is. But that map is a snapshot, not a story. It's a single frame taken from a film that has been playing for more than 4 billion years. If you could reach into that map and pull time backward, even just a little, the shapes would start to blur. Coastlines would soften like wet ink on paper. Islands would slide toward continents. Seas would narrow, then disappear. The world, it turns out, has never been very good at staying still. Long before Antarctica became the isolated, ice-bound land we know today. It was part of a much larger arrangement, one that makes our modern maps look almost misleading. To see it clearly, you have to imagine the Earth not as a globe divided into neat countries and oceans, but as a living surface, constantly rearranging itself in slow, deliberate motions that are almost impossible to notice within a single human lifetime. The key to this moving puzzle lies beneath your feet, wherever you happen to be listening from. The ground feels solid, dependable, like the most reliable thing in your day. Yet far below that surface, the Earth is warm, restless, and in motion. Heat from the planet's core rises upward, creating slow currents in the mantle, the thick layer of semi-molten rock beneath the crust. Floating on top of that layer are the tectonic plates, enormous slabs of solid rock that carry the continents and oceans with them. These plates don't glide smoothly like skaters on ice. They push, pull, collide, and sometimes tear apart. When they collide, mountains rise. When they pull apart, new oceans form. When one slides under another, volcanoes and deep ocean trenches appear. It's a system that runs quietly in the background, shaping the surface of the planet over spans of time so long they almost defy imagination. Antarctica's role in this system has been anything but passive. If you wind the clock back around 200 million years, you find a very different world. The continents were joined together in a vast supercontinent called Panga. From pole to pole, nearly all the land on Earth was connected in one massive shape, surrounded by a single global ocean. In that ancient configuration, there was no separate Antarctica. At the bottom of the world, there was simply a southern portion of Panga, a stretch of land that would one day become several different continents. Over time, Panga began to crack like a piece of drying clay. The first major split separated the northern land mass, Laurasia, from the southern one, Gondwana. It was within Gondwana that the future Antarctica found its early neighbors. Gondwana was a giant sprawling continent made up of what would later become South America. Africa, India, Australia, and Antarctica itself. These lands were stitched together, sharing mountain ranges, river systems, and ecosystems. If you had stood on what is now the Antarctic Peninsula back then, you could have walked in theory all the way to what is now southern South America without ever stepping into the ocean. As Gondwana began to break apart, the pieces didn't all drift away at once. The process unfolded in stages like a slow dance where partners gradually let go. Africa moved northward. India set off on a long journey toward Asia. Australia and Antarctica stayed connected for much longer, lingering together as a combined land mass near the southern latitudes. During this time, Antarctica's position on the globe was very different from what we see on modern maps. It wasn't centered directly over the South Pole. Instead, it sat farther north, angled in a way that allowed it to receive more sunlight throughout the year. That extra light, combined with a generally warmer global climate, helped support the forests and ecosystems that once covered large parts of the continent. If you were to draw a map of the world from that period, it would look unfamiliar, even confusing. The familiar outlines we recognize today wouldn't be there. Instead, you'd see a broad southern land mass stretching across what is now half the globe with shallow seas cutting into it, and mountain chains marking the seams where plates were beginning to pull apart. As millions of years passed, the gaps widened. Oceans formed in the spaces between the drifting continents. The South Atlantic opened up between Africa and South America. The Indian Ocean expanded as India raced northward. And slowly, almost reluctantly, Antarctica began to part ways with Australia. That final separation was a turning point, not just for the map, but for the climate of the entire planet. Once Antarctica was completely surrounded by water, a continuous ocean current could form around it. This current, driven by strong winds and the rotation of the Earth, began to flow endlessly in a loop, cutting the continent off from warmer waters to the north. From a mapmaker's perspective, this might seem like a simple change, just another line of blue drawn around a white shape. From the planet's perspective, it was a major shift in how heat was distributed. Warm ocean water that once flowed toward Antarctica was now deflected away. Cold water began to dominate the region. The stage was set for ice to take over. Yet, even as Antarctica settled into its new, more isolated position, the land itself continued to change. Beneath the growing ice sheets, the tectonic plates were still moving. Mountains rose and eroded. Valleys formed. In some places, the weight of the ice pushed the crust downward, creating deep basins that now sit far below sea level, hidden under kiln of frozen water. Modern technology has given us a way to peek beneath that ice and see what the continent really looks like. Using radar, gravity measurements, and seismic waves, scientists have mapped the hidden landscape of Antarctica in surprising detail. What they found is not a simple flat slab of rock, but a complex terrain with rugged mountain ranges, winding valleys, and vast lands. One of the most striking features is a massive mountain chain called the gambuts of mountains buried deep beneath the East Antarctic ice sheet. These mountains are roughly the size of the European Alps. Yet they're completely invisible from the surface. They sit under so much ice that if you didn't know they were there, you'd never guess the continent hides such dramatic relief. This hidden topography is a reminder that Antarctica's story didn't end when it froze over. The map we see today is still being shaped by forces we can't easily observe. The ice flows slowly, but relentlessly like a frozen river. It grinds down rock, carries sediment, and reshapes the land beneath. In some places, it even creates lakes under the ice. Bodies of liquid water kept warm by heat from the Earth's interior and the immense pressure of the ice above. These subglacial lakes are another detail that makes the modern map feel incomplete. On the surface, Antarctica looks like a single solid mass of ice. Beneath, it's dotted with hundreds of lakes connected by networks of channels that move water slowly across the hidden landscape. It's a quiet, dark hydrological system operating out of sight, adding another layer of complexity to a continent that already defies simple description. If you compare an ancient map of Gondwana to a modern satellite image, the difference is dramatic, but the connections are still there if you know where to look. Mountain ranges that once ran across multiple continents now appear as separate fragments on opposite sides of oceans. Rock formations in Antarctica match those in South America, Africa, and Australia, like pieces of a puzzle that were pulled apart and scattered. Even the fossils tell this story. Identical species of ancient plants and animals have been found in places that are now separated by thousands of km of ocean. The only way to explain that pattern is that those lands were once connected, allowing life to spread across them before the slow pull of tectonics carried them away from each other. This is where the idea of a map that doesn't quite make sense anymore becomes more than just a poetic notion. The map we use every day is a practical tool designed for navigation, politics, and geography as it exists right now. It doesn't show the scars of ancient collisions or the outlines of long-lost continents. It doesn't hint at the journeys the land itself has taken. In some ways, our modern view of the world flattens its history. We see borders and coastlines as fixed, even though they're just temporary arrangements in a much longer process. Antarctica's position at the bottom of the globe feels natural to us because it's all we've ever known. But from the planet's point of view, it's a relatively recent development. The idea that the South Pole hasn't always been covered in ice can be unsettling at first. It challenges a deep-seated image of what Earth is supposed to look like. Yet when you step back and consider the immense time scales involved, it starts to feel almost inevitable. Given enough time, almost any arrangement of land and sea is possible. As you sit with that thought, it might be interesting to reflect on how small our own sense of time is. By comparison, a human lifetime, even a long one, is barely a blink in the history of a continent. The maps we grow up with can remain unchanged for centuries, while the ground beneath them is quietly on the move, shifting in ways that will only become obvious long after we're gone. This doesn't mean our maps are wrong. They're just incomplete. They tell us where things are now, not how they got there or where they might be going next. Antarctica, in particular, is a reminder that some of the most important parts of the story are hidden, either under ice, underwater, or under layers of time we don't usually think about. There's something quietly fascinating about that. The idea that a place we associate so strongly with stillness and permanence is in fact the product of endless motion. That the frozen edge of the world is also a traveler, one that has crossed climates, latitudes, and entire geological eras to arrive where it is today. Long before the first sheet of ice crept across the southern land, long before the word Antarctica meant cold wind and endless white, this part of the world lived under a very different sky. The sun still followed its strange polar path, circling low in summer and disappearing for months in winter. But its warmth carried more weight. The air held heat instead of a sharp edge. The ground, instead of being sealed under frozen water, was open to rain, roots, and the slow work of living things. To picture this version of the continent, it helps to step out of our modern expectations for a moment. We tend to link latitude directly with temperature. North is cold, south is cold, the middle is warm. It's a neat, simple rule, and for today's world it mostly works. But Earth's climate has not always followed that pattern. The planet's atmosphere, the way heat moves through the oceans, the arrangement of continents, and even the composition of the air itself have all shifted over time. When those pieces line up differently, the familiar climate zones blur and rearrange. During several long stretches of Earth's past, the planet existed in what scientists call a greenhouse state. This doesn't mean there were literal greenhouses spread across the land, of course, but it does mean that the atmosphere trapped much more heat than it does today. Levels of carbon dioxide were higher. There were no permanent ice caps at either pole. The difference in temperature between the equator and the poles was much smaller than what we experience now. Heat moved more evenly around the globe. In that kind of world, being close to the South Pole didn't automatically condemn a place to deep freeze. Instead, Antarctica found itself in a cool, temperate zone, more like the southern reaches of modern-day New Zealand or Patagonia, rather than the icy desert we know today. The warmth didn't arrive all at once, and it didn't vanish suddenly either. It came and went in waves, rising and falling over tens of millions of years. Some of the warmest periods occurred during the Cretaceous and early Paleogene, roughly between 140 million years ago. At that time, the world was shaped by a combination of high greenhouse gas levels, different ocean currents, and continents that were still in the middle of their slow rearrangement. What did that warmth feel like on the ground? We can't step back in time, but the land left behind a set of clues that allow scientists to make careful, informed guesses. Fossilized plant remains are among the most telling. Leaves, in particular, carry a lot of information. The shape of a leaf, the thickness of its veins, the size and spacing of tiny pores called stomata. All of these features are influenced by temperature, sunlight, and the amount of carbon dioxide in the air. When researchers find fossil leaves in Antarctic rock, they don't just look at them as isolated objects. They compare them to modern plants growing in known climates. By matching patterns, they can estimate the range of temperatures and rainfall that would have supported those ancient species. What they've found is surprisingly consistent. Much of Antarctica once supported forests made up of trees related to species that now grow in the southern hemisphere, such as southern beeches and conifers similar to modern pines and araucarias. These weren't tropical jungles dripping with vines and oversized leaves, but they were real forests with canopies, undergrowth, and a mix of plant life filling different layers of the ecosystem. Temperatures in some regions may have hovered around 10 to 15 degrees C during the warmest months, sometimes even higher. Winters, while dark and cooler, were not cold enough to maintain permanent ice. Snow may have fallen, but it melted away when the sun returned. Rain played a role too. Ancient soils and sediment layers suggest that parts of the continent experience regular rainfall, enough to feed rivers and wetlands. These waterways carve channels into the land, carrying sediment toward the coast, building floodplains and creating habitats for a range of plants and animals. The idea of rivers flowing freely across Antarctica feels almost unreal when you think about the modern landscape. Today, most of the water there is locked up in ice. And what little liquid water exists often flows beneath the ice sheets, hidden from view. But in that warmer world, water moved across the surface, shaping the land in visible, familiar ways. One of the most intriguing pieces of evidence for this comes from the shapes of valleys buried under the ice. Using radar and seismic surveys, scientists have mapped networks of channels that look very much like river systems. These aren't the kinds of features glaciers usually carve. They have branching patterns, gentle curves, and slopes that suggest long-term erosion by flowing water. In some places, these ancient river valleys run for hundreds of km, stretching from the interior of the continent toward what would have been its ancient coast. They hint at a landscape that once had a functioning water cycle complete with rainfall, runoff, and drainage systems, much like the ones we see on other continents today. Along those rivers, life found a foothold. Fossils of freshwater organisms, including small crustaceans and plants adapted to wet environments, have been discovered in Antarctic rock. These finds paint a picture of lakes and slow-moving streams where life could thrive, at least during the warmer parts of the year. And then there were the animals that walked on land. Dinosaurs are the most famous of these, and their presence in Antarctica often surprises people. But during the warm periods, there was nothing particularly extreme about living at high latitudes as long as temperatures stayed moderate. Some of the dinosaur fossils found there belong to planting species that likely fed on the forests and shrubs growing across the landscape. There is also evidence of predators, though their reminiscences are rarer. The challenge for these animals wouldn't have been the cold, but the light. Even in a warm climate, Antarctica still experienced long periods of darkness each year. During the winter months, the sun would dip below the horizon and not return for weeks, sometimes months, depending on how far south a particular region lay. Plants and animals had to adapt to that rhythm. Trees may have shed their leaves in winter, much like deciduous trees do in temperate zones today. Some animals might have migrated northward during the darkest months, while others could have hunkered down, slowing their metabolism or relying on stored energy to get through the lean season. The exact strategies are still a matter of research and debate, but the presence of complex life suggests that workable solutions existed. It's also worth remembering that Antarctica didn't exist in isolation during this time. It was still connected, or at least close to other southern continents. Australia in particular remained attached to Antarctica until around 45 million years ago. This connection allowed plants and animals to move between the two, sharing genetic lineages and helping populate both lands with similar species. That link also influenced the climate. Warm ocean currents could reach the southern coasts more easily, carrying heat from lower latitudes. The presence of a large, connected landmass affected wind patterns and rainfall, creating regional climates that would have felt more familiar to a modern visitor than today's extreme conditions. As you imagine this world, it might help to think of Antarctica not as a singular uniform place, but as a continent with regional variation, just like any other coastal areas would have been milder and wetter, influenced by the nearby ocean. Interior regions might have been cooler and drier, especially during the long winters. Mountains would have created rain shadows, valleys would have collected water, and different ecosystems would have found their own niches across the landscape. Over time, though, the balance began to shift. The same tectonic movements that carried Antarctica southward also altered its connections to the rest of the world. As Australia drifted away and South America finally separated, the pathways for warm water closed off. At the same time, global levels of carbon dioxide began to decline, slowly reducing the greenhouse effect. The reasons for this are complex and involve a mix of volcanic activity, weathering of rocks, and the long-term burial of carbon in sediments and living organisms. Whatever the exact combination of causes, the result was a gradual cooling of the planet. For Antarctica, this cooling was amplified by its position. Once it was fully surrounded by ocean, a powerful current could circle the continent without being interrupted by land. This current effectively isolated Antarctica, preventing warmer waters from reaching its shores. The air above cooled. Snow lingered longer. The first permanent ice began to form in high, elevated regions. In this transitional period, the continent likely experienced a patchwork of conditions. Some areas still supported forests and flowing rivers, while others, particularly at higher elevations, began to see year-round snow and small glaciers. It would have been a landscape in flux, with boundaries between green and white shifting over thousands of years. There's a subtlety to this phase that often gets lost when we talk about ice ages and warm periods, as if they are simple binary states. In reality, climate change at this scale is more like a long, uneven fade. Temperatures don't drop everywhere at once. Ecosystems don't disappear overnight. They retreat, adapt, and sometimes hold on in sheltered pockets long after the broader trend is turned against them. In Antarctica, this may have meant that forests persisted in certain coastal regions or low-lying areas, even as glaciers expanded elsewhere. Small refuges of plant and animal life could have survived for extended periods, gradually shrinking as the cold advanced. Eventually, though, the tipping point was reached. Ice sheets grew large enough to influence the climate themselves. Ice reflects sunlight, sending a significant portion of it back into space rather than absorbing it as heat. As more of the continent became covered in ice, this reflective effect increased, reinforcing the cooling trend. The warmer sun that once nourished forests and rivers became a weaker presence, especially during the long winters. The seasonal rhythm shifted. Summers grew shorter and cooler. The snow that fell each winter began to survive into the next year, adding to a growing permanent ice cover. Still, the memory of that warmer world never fully vanished. It remains written into the rocks, the shape of buried valleys, and the chemical signatures locked into ancient sediments. Every fossil leaf, every grain of pollen preserved in stone, is a small reminder that Antarctica's story includes more than just ice and cold. As you listen, you might notice how this slow transformation echoes patterns we see elsewhere in nature, even on much smaller scales. A forest gives way to a meadow. A river changes course. A shoreline erodes and reforms. These changes usually happen gradually, often unnoticed, until the difference becomes obvious. On a planetary scale, the same principle applies, just stretched across spans of time that dwarf human experience. The warmer sun over ancient Antarctica didn't vanish in a dramatic moment. It faded little by little as the planet system shifted around it. What makes this story especially compelling is that it sits at the intersection of so many forces. The movement of continents, the chemistry of the atmosphere, the circulation of the oceans, and the adaptability of life itself all played a role. None of these acted alone. Each influenced the others, creating a complex web of cause and effect that ultimately reshaped an entire continent. And even now, in the present day, those forces are still at work. Antarctica remains a sensitive part of the global climate system. Changes in ocean temperature and atmospheric composition continue to influence the stability of its ice sheets. The continent that once lived under a warmer sun is in a sense still responding to the balance between warmth and cold, just in a different phase of its long journey. Beneath the vast pale surface that defines Antarctica today, beneath the wind-sculpted snow and the slow-flowing rivers of ice, there is another landscape that rarely enters our everyday picture of the world. It is not a place you can walk through or see with your own eyes, at least not yet. It exists in fragments, in hints and outlines, in data traced by instruments, and in physical pieces of the past brought up from deep within the ground. This hidden world is the quiet record of forests that once grew where ice now stands several km thick. To understand how scientists even begin to talk about forests under an ice sheet, it helps to think about the ice itself not as a solid, unchanging lid, but as something more like a very slow, very heavy river. Over time, ice flows outward from the high interior of the continent toward the coasts. As it moves, it can pick up pieces of rock, soil, and anything else it passes over. Those materials get carried along, sometimes for great distances, before they are dropped at the edges of the ice or exposed by melting. Every so often, this process delivers something unexpected. A fragment of wood, a leaf impression, a grain of pollen. Each one is a small physical connection to a world that no longer exists on the surface. When researchers find these pieces, often in places where the ice meets the ocean or where strong winds have scoured the surface clean, they become starting points for much larger questions. One of the most striking discoveries has been fossilized wood found in Antarctica. Not just small bits or vague traces, but recognizable pieces of tree trunks complete with growth rings. Those rings, like the ones you see in a freshly cut log, tell a story of seasons. Each ring represents a year of growth, with thicker, lighter bands formed during periods of active growth and thinner, darker bands marking times of slower development. By counting and measuring these rings, scientists can learn how fast those ancient trees grew and how long they lived. Fast growth suggests relatively mild supportive conditions. The presence of clear seasonal patterns points to a climate that, while warm enough to support forests, still experience significant changes over the course of a year. The trees themselves appear to have been similar to species that now live in the southern hemisphere, particularly in places like southern South America, New Zealand, and Australia. Some were conifers related to modern pines and arcyras. Others were broadleaf trees, including early relatives of the southern beech. These forests were not isolated patches. Evidence suggests they covered large areas of the continent, forming connected ecosystems that stretched across valleys and hills. Underneath the canopy, there would have been shrubs, ferns, and ground plants, all part of a layered environment that supported insects, small animals, and the larger creatures that move through it. Of course, finding a piece of wood or a leaf doesn't tell you exactly where the tree once stood. That's where other tools come in. One of the most powerful methods for uncovering the hidden past of Antarctica is something called ice-penetrating radar. This technology sends radio waves down through the ice and measures the signals that bounce back from the rock and sediment below. By moving radar instruments across the surface, often mounted on aircraft or sleds, scientists can build up a three-dimensional picture of what lies beneath. They can see the shapes of valleys, ridges, and basins. They can identify areas where the bedrock is smooth and flat, and others where it is deeply carved. When these underground maps show networks of channels that branch and curve like river systems, it strengthens the case for a landscape shaped by flowing water rather than ice alone. Glaciers tend to carve broad U-shaped valleys. Rivers cut narrower, more winding paths. In many parts of Antarctica, the hidden terrain looks much more like the latter. These buried river valleys would have been natural gathering points for forests. Water supports plant growth, and floodplains often develop rich soils, as rivers deposit layers of sediment over time. In a warmer Antarctic climate, these areas could have supported dense vegetation with trees growing along the banks and spreading outward across the surrounding land. Another line of evidence comes from microscopic fossils, especially pollen. Pollen grains are incredibly durable. They have tough outer shells designed to survive the journey from a plant to wherever they eventually land. Because of that, they can persist in sediments for millions of years. When scientists drill into rock layers or ancient sediment beneath the ice, they often find these tiny grains preserved in remarkable detail. By identifying the types of pollen, researchers can tell which kinds of plants were growing nearby at the time the sediment was laid down. In Antarctic samples, pollen from trees and other land plants appears in layers that date back to the continent's warmer periods. The variety and abundance of these grains suggest not just scattered vegetation, but thriving plant communities. What makes this especially interesting is how these findings line up with data from other continents that were once connected to Antarctica. Similar pollen types and plant fossils appear in southern South America, Africa, and Australia from the same geological periods. This supports the idea that these lands shared ecosystems when they were part of Gondwana. As you imagine these forests, it's worth considering what forest means in this context. It's easy to picture something like a modern tropical rainforest, dense, humid, and dripping with vines. But the ancient forests of Antarctica were likely different in character. They would have existed in a high-latitude environment, which means they had to deal with long periods of darkness each year. During the winter months, the sun would stay below the horizon, plunging the land into a prolonged night. Even in a warm climate, that lack of light would have limited plant growth. So instead of year-round lushness, these forests probably followed a strong seasonal rhythm. During the long summer days when the sun circled low in the sky without setting, plants would have had extended periods of light to fuel rapid growth. Trees might have put on most of their annual growth in a relatively short window, taking advantage of the continuous daylight. Then, as winter approached and the light faded, growth would slow or stop. Leaves might fall. Animals would shift their behavior, perhaps migrating or reducing their activity. The forest would enter a kind of extended pause, waiting for the sun's return. That cycle is reflected in the growth rings of fossilized wood. The pattern suggests bursts of growth followed by periods of dormancy, a clear sign of seasonal change, even in a generally warm world. Beyond plants, the forests would have supported a range of animals, many of which are known only from fragmentary remains. Insects, for example, are rarely preserved as fossils, but their presence is implied by the kinds of plants that grew there. Flowering plants, which appear in later periods of Antarctica's warm history, often rely on insects for pollination. Small reptiles, amphibians, and early mammals may have lived in the undergrowth, feeding on insects and plants. Larger herbivores, including dinosaurs in earlier periods, would have moved through the forests, browsing on leaves and branches. The presence of these animals would have influenced the shape and composition of the forest itself. Grazing and browsing can change which plants dominate an area. Animals also help spread seeds, carrying them in their fur or digestive systems to new locations. In this way, the forest and its inhabitants would have been part of a connected, evolving system. One of the more subtle clues about these ecosystems comes from the chemistry of ancient soils. In some places, layers of sediment beneath the ice show signatures that suggest the presence of organic matter. This kind of material forms when plants grow, die, and decompose, adding carbon and other elements to the soil. By analyzing these layers, scientists can estimate how productive the land was. Higher levels of organic material point to more abundant plant growth. In parts of ancient Antarctica, those levels are comparable to what you might find in modern temperate regions. It's also possible to look at isotopes, different forms of the same chemical elements, to infer details about temperature and rainfall. For example, the ratio of certain oxygen isotopes in minerals can indicate the temperature of the water that was present when those minerals formed. These measurements often line up with the picture painted by plant fossils and pollen, reinforcing the idea of a relatively mild wet climate. All of this information comes together to form a layered understanding of the hidden forests. No single piece of evidence tells the whole story. A leaf fossil suggests a type of tree. Pollen grains hint at the broader plant community. Buried valleys point to rivers that supported growth. Chemical signatures in the soil give clues about productivity and climate. Each one adds another brush stroke to a picture that is still being filled in. What's especially striking is how much of this story is still physically present beneath the ice. The ice sheets didn't grind the land down to nothing. In many areas, they preserved it, sealing off valleys, soils, and sediments in a cold, stable environment. This means that Antarctica holds one of the best-kept archives of Earth's ancient ecosystems. In other parts of the world, forests have been replaced, eroded, and built over again and again. In Antarctica, the deep freeze locked much of the landscape in place, slowing the processes that would normally destroy or obscure these records. Drilling projects have begun to tap into this archive more directly. By boring through the ice and into the sediments below, scientists can retrieve cores that contain layers of material laid down over millions of years. These cores are like timelines, with the oldest layers at the bottom and the youngest near the top. Within them, researchers find shifts from organic-rich sediments associated with plant growth and flowing water to more barren layers that reflect the advance of ice and colder conditions. Each transition marks a step in the long process that turned a green continent into a frozen one. There's also a sense of scale to this that can be hard to fully grasp. The ice sheet in East Antarctica, for example, is in some places more than 4 km thick. That means the ground below hasn't seen sunlight in millions of years. The last time those buried forests were exposed to the air, the world above them looked completely different. Human beings did not exist. Most modern animal species had not yet evolved. The continents were arranged in unfamiliar ways. The sky itself may have looked different, with different patterns of stars visible from that part of the world. And yet here we are in the present, able to detect and study the traces of that ancient world, using instruments and methods developed over just the past few decades. There's something quietly remarkable about that connection across time. As you listen, you might imagine those hidden forests not as something lost forever, but as something resting, preserved in a kind of deep frozen pause. They're not alive, of course, but the information they carry is still active, still shaping our understanding of how the planet works. This understanding has practical importance, too. By studying how Antarctica responded to past periods of warmth, scientists can learn about the conditions that lead to the growth or retreat of ice sheets. That knowledge helps inform models of how the continent might respond to changes happening today. The ancient forests tell us that Antarctica is not inherently a land of ice. It became that way under specific circumstances. Those circumstances can, in theory, change again, though the time scales and pathways may be very different. For now, though, the forests remain where they are beneath the ice, silent and unseen. They are part of the continent's deeper memory, a layer of history that sits below the more visible story of glaciers, storms, and cold oceans. If you could somehow peel back the ice like a heavy frozen blanket and look down at the bare ground of Antarctica, what you would see would not be a flat, empty slab of rock. You would see a landscape that looks in many ways familiar. There would be long valleys stretching across the continent, winding channels carved into bedrock, broad lands that once held water, and ridges that rise like the spines of buried hills. This hidden terrain tells a story not of stillness, but of movement, of water that once flowed freely across a place now locked in ice. Long before glaciers claimed the surface, Antarctica was shaped by the same forces that shape landscapes everywhere. Rain fell, snow melted. Water gathered in small streams that joined into larger rivers. Those rivers followed the natural slopes of the land, wearing away rock and soil, carrying sediment toward the sea. Over thousands and millions of years, they carved paths that grew deeper and wider, forming valleys and flood plains. The idea of rivers in Antarctica can feel strange at first, almost like a contradiction. Today, liquid water is rare on the surface. When it does appear, it's usually in the brief narrow window of summer, trickling over ice or pooling in shallow meltwater ponds before freezing again. But in a warmer past, water was a constant presence. Rainfall patterns would have varied from region to region, influenced by mountains, proximity to the ocean, and prevailing winds. Coastal areas likely received more moisture, while interior regions may have been drier, especially during certain seasons. Even so, the overall climate allowed water to flow across the land for long periods, not just in short bursts. One of the clearest pieces of evidence for this comes from the shapes of the valleys hidden beneath the ice. Using radar and seismic imaging, scientists have mapped large portions of Antarctica's subglacial topography. The patterns they see often resemble river networks found on other continents. These networks branch outward with smaller channels feeding into larger ones, forming tree-like patterns that are characteristic of erosion by flowing water. Glaciers, by contrast, tend to carve broad, smooth, U-shaped valleys. While Antarctica certainly has those, too, especially from more recent glacial activity, many of the deeper, more intricate channel systems appear to predate the ice. In some regions, these buried valleys are immense. They stretch for hundreds of km, cutting across the continent in ways that suggest they once drained vast areas of land. These were not small streams. They were major river systems comparable in scale to some of the large rivers we see today. Imagine standing on the bank of one of these ancient rivers. The water would move steadily past, carrying bits of sand, leaves, and soil. In the distance, the land would slope gently downward toward the coast, where the river would eventually meet the sea. Along its edges, plants would grow, roots reaching into the moist soil. Animals would come to drink, to hunt, to cross from one side to the other. The presence of such rivers also implies the existence of lakes. Rivers don't just flow straight to the ocean. They often collect in basins, forming lakes where the land dips or where natural barriers slow the movement of water. In Antarctica's hidden landscape, scientists have identified numerous low-lying areas that could have served as ancient lake beds. Some of these basins are now home to subglacial lakes, bodies of liquid water trapped beneath the ice. They're kept from freezing by a combination of geothermal heat from the earth below and the immense pressure of the ice above. While these modern lakes are not direct survivors of their ancient counterparts, they often occupy the same depressions in the land. The shape of these basins, along with the sediments found in them, suggest they once held open water. Layers of fine-grained material such as silt and clay are typical of lake environments where particles settle slowly to the bottom in calm conditions. In some cores drilled from beneath the ice, researchers have found exactly these kinds of layers stacked one on top of another like pages in a long, quiet book. Within those layers, there are often traces of organic material, bits of plant matter, microscopic remains of algae, chemical signatures that point to biological activity. These are the kinds of things you expect to find at the bottom of a lake, where life in the water and along the shoreline leaves behind a steady rain of material that settles into the sediment. Taken together, the rivers and lakes paint a picture of a connected water system. Rain and snow melt would feed streams in the highlands. Those streams would join into rivers that flowed through valleys and across plains. Along the way, water would collect in lakes, sometimes spilling over their edges to continue downstream. This system would have shaped the land in very specific ways. Floodplains would develop along river banks where seasonal floods deposited fresh layers of sediment. These areas tend to be especially fertile, supporting dense plant growth. Over time, rivers might change course, leaving behind abandoned channels and creating a patchwork of wetlands and dry ground. The presence of these features beneath the ice tells us that Antarctica's surface was once dynamic and varied. It wasn't a uniform expanse of forest or grassland. It was a mosaic of environments shaped by elevation, water availability, and underlying geology. Mountains played an important role in this. Antarctica is home to several major mountain ranges, some of which are still visible above the ice today, like the Trans-Antarctic Mountains. Others, such as the Gambits Mountains, are completely buried. These mountains would have influenced where rivers formed and how they flowed. Rainfall patterns tend to change around high terrain. One side of a mountain range often receives more precipitation as moist air rises and cools, while the other side lies in a rain shadow and remains drier. Rivers would have originated in these wetter regions, cutting their way down slopes and through valleys. Over time, they would carve deep channels, especially in areas where the rock was softer or fractured. As rivers carried sediment toward the coast, they would have built deltas where they met the sea. These are flat fan-shaped areas formed by layers of deposited material. Deltas are often rich in nutrients and support diverse ecosystems. While direct evidence of ancient Antarctic deltas is harder to come by due to the way coastlines have shifted and been eroded or buried by ice, the presence of large river systems makes their existence likely. The coastline itself would have looked very different. Sea levels during warmer periods were often higher than they are today. With no massive ice sheets locking up water, more of it remained in the oceans. This would have pushed the shoreline farther inland in many places, creating shallow seas, bays, and estuaries where fresh water and salt water mixed. These coastal zones would have been especially productive environments. They often support dense plant growth and serve as nurseries for many types of animals. In ancient Antarctica, they may have been among the richest parts of the ecosystem. All of this movement of water and sediment would have left a layered record in the ground. Over time, river deposits, lake sediments, and coastal materials would pile up, creating thick sequences of rock. Later, when the climate cooled and ice began to spread, these layers were sealed away, protected from further erosion. This is why drilling into the sediments beneath the ice can reveal such a detailed history. Each layer corresponds to a different period, a different set of conditions. By analyzing the composition of these layers, scientists can tell whether the environment at the time was wet or dry, warm or cool, rich in life or relatively barren. One of the tools used in this analysis is the study of isotopes. Certain elements like oxygen and carbon come in slightly different forms known as isotopes. The ratios of these isotopes in minerals and organic material can change depending on temperature and the type of water present when the material formed. For example, water that evaporates and falls as rain carries a different isotopic signature than water that freezes into ice. By measuring these signatures in sediment layers, researchers can infer whether the water in an ancient lake came mostly from rainfall, snow melt, or other sources. These details help build a more complete picture of how Antarctica's water system functioned. They suggest not just the presence of rivers and lakes, but the rhythms of precipitation and runoff that sustain them. It's also important to consider the role of time in shaping this landscape. Rivers don't carve deep valleys overnight. It takes thousands of years for a small stream to cut a noticeable channel and millions of years to form a major river valley. The depth and extent of the buried channels in Antarctica indicate that flowing water shaped the land for a very long period. This means that the warmer conditions that allowed these rivers to exist were not brief or fleeting. They persisted long enough for entire drainage systems to develop and mature. Forests grew along their banks. Lakes filled and emptied. Sediments accumulated layer by layer. Eventually, as the climate cooled, this system began to change. Snow that once melted in summer started to linger. Small glaciers formed in high mountain valleys. Over time, these glaciers grew and flowed outward, following many of the same paths that rivers had once taken. In a sense, the ice inherited the old river valleys. It filled them, flowed along them, and in some cases reshaped them further. This is one of the reasons why modern ice flow patterns often align with ancient drainage systems beneath the surface. This continuity is a quiet but powerful idea. The landscape doesn't simply reset when conditions change. New processes build on the foundations left by old ones. The paths carved by water became pathways for ice. The basins that held lakes became places where subglacial water now collects. There's a kind of layered memory in the land itself. Each phase of Antarctica's history leaves traces that influence what comes next. As you sit with this image of ancient rivers and lakes, it might be interesting to think about how much of the world around you carries similar hidden stories. The river near your home, if there is one, likely follows a path shaped by ice, water, and shifting ground over thousands of years. The hills and valleys you see are the product of long, patient processes that far outlast any single human generation. Antarctica's difference is not in the kinds of forces that shaped it, but in how well those forces have been preserved. The ice, as for all its power, has also acted as a protective cover, keeping much of the older landscape intact. This makes the continent a unique archive of how land and water interact under different climate conditions. By studying it, scientists can test their understanding of erosion, sediment transport, and the development of drainage systems. They can see how rivers respond to changes in temperature and precipitation, and how quickly landscapes can transform when ice takes over. These insights don't just apply to the distant past. They help inform models of what might happen in the future. As parts of the world warm or cool, as ice advances or retreats, the movement of water across the land will change. Rivers may shift course. New lakes may form. Old ones may drain or disappear. In Antarctica, there is already evidence of this kind of change happening on smaller scales. Subglacial lakes can suddenly drain, sending pulses of water beneath the ice toward the coast. These events can influence how fast glaciers move, which in turn affects how much ice reaches the ocean. The ancient landscape beneath the ice plays a role in guiding these modern processes. Valleys and channels carved by rivers millions of years ago now direct the flow of water under the ice sheet. In this way, the past and the present are connected in very direct physical terms. At some point, when you step far enough back from the details of rivers and forests, from leaves and lake beds and growth rings in ancient wood, a broader pattern begins to emerge. All of those things, as vivid and tangible as they are, existed on a piece of land that was itself in motion. Not fast, not in any way you could feel under your feet, but steadily, persistently, and without pause. Antarctica's story is not just about what happened on its surface. It is also about where that surface was and where it was going. The idea that continents move was once considered strange, even laughable. For much of human history, the shapes of the continents were treated as permanent features of the world, like the stars in the sky. Maps were updated for political reasons, for newly discovered coastlines for better measurements. But the underlying assumption was that the land itself stayed put. That assumption began to crack in the early 20th century when a German scientist named Alfred Weir looked at a world map and noticed something that once seen is hard to unsee. The coastlines of South America and Africa seemed to fit together, almost like pieces of a broken plate. He proposed that the continents had once been joined and had since drifted apart. At the time, his idea was controversial. He didn't have a clear explanation for how entire continents could move. The forces he suggested seemed too weak. But over the following decades, as scientists learned more about the structure of the ocean floor and the behavior of Earth's interior, the pieces began to fall into place. The theory of plate tectonics emerged, providing a framework that explained not just drifting continents, but earthquakes, volcanoes, mountain ranges, and the creation and destruction of ocean basins. In this framework, Antarctica is not a static land mass sitting quietly at the bottom of the world. It is a passenger on a massive tectonic plate, one of several that together form the outer shell of the planet. This plate, like the others, floats on the slowly moving mantle below. Heat from the Earth's interior drives convection currents in that mantle, and those currents in turn push and pull the plates above. The movement is subtle. On average, tectonic plates shift at rates of a few cm per year, roughly the same speed at which your fingernails grow. That doesn't sound like much. In a human lifetime, it amounts to a few meters at most. But over millions of years, those centimeters add up to thousands of kilometers. Antarctica's journey began when it was still part of Gondwana, the great southern supercontinent. At that time, it was surrounded by neighbors on nearly all sides. To the west lay what would become South America. To the north and northeast were Africa and India. To the east and southeast was Australia. All of these lands shared geological features, ecosystems, and climate patterns. The first major shift came as Gondwana began to break apart. The cracks didn't open all at once. They spread slowly, guided by weaknesses in the crust and the movement of the mantle below. Africa and South America were among the first to part ways, opening the early South Atlantic Ocean between them. India peeled away and began its rapid northward journey toward Asia, a collision that would eventually give rise to the Himalayas. Australia and Antarctica, however, lingered together for much longer. Their connection would play a crucial role in shaping Antarctica's climate and environment. During this long period of attachment, the combined land mass sat in southern latitudes, but not as far south as Antarctica does today. This position allowed it to receive more direct sunlight and to stay connected to warmer ocean currents. The climate, while still influenced by seasonal changes in light, remained mild enough to support the forests and river systems we've already explored. As time went on, though, the forces pulling the continents apart continued their quiet work. The rift between Australia and Antarctica widened. What began as a series of cracks and shallow seas gradually deepened into a full ocean basin. By around 45 million years ago, the two land masses were finally separated. This separation marked a turning point, not just in terms of geography, but in the way heat moved around the planet, with Australia drifting northward and Antarctica left behind. A new uninterrupted pathway opened up for ocean currents to flow around the southern continent. The formation of this circular current, which today is known as the Antarctic Circumpolar Current, changed the rules of the climate system in the region. Unlike other ocean currents, which are deflected by continents, this one could flow endlessly around the globe, driven by strong westerly winds. As it strengthened, it effectively isolated Antarctica from warmer waters to the north. The ocean around the continent grew colder. The air above it followed suit. This shift didn't happen overnight. It unfolded over millions of years, but its effects were profound. At the same time, Antarctica itself continued to drift. The tectonic plate carrying it moved farther south, nudging the continent closer to the South Pole. This change in latitude meant that the angle of sunlight reaching the surface became lower, reducing the amount of energy absorbed during the year. Even small changes in sunlight can have large effects over long periods. Less energy means cooler temperatures. Cooler temperatures allow snow to last longer on the ground. Snow that doesn't melt can compact into ice. Ice reflects sunlight, sending it back into space and reinforcing the cooling trend. This combination of factors, ocean isolation, and a shift in latitude, worked together to push Antarctica toward a colder state. But the continent's movement wasn't just a straight slide southward. It also involved rotation and subtle changes in orientation. If you look at reconstructions of Antarctica's past positions, you can see that the continent has slowly turned over time, changing which regions faced the sun more directly and which were tucked into deeper shadow. These changes would have influenced regional climates, making some areas cool faster than others. Mountains and valleys would have responded differently to these shifts. Higher elevations tend to cool more quickly and hold on to snow longer. Low-lying coastal regions, especially those still influenced by relatively warm ocean waters, may have remained ice-free for longer periods. This created a patchwork of conditions across the continent during its transition from green to white. Some regions likely supported forests and flowing rivers, even as glaciers began to form elsewhere. Over time, those glaciers grew, flowed downhill and merged gradually, covering more and more of the land. The movement of the continent also affected the way its interior responded to the growing weight of ice. As ice sheets thickened, they pressed down on the crust beneath them. This process, known as isodic adjustment, caused parts of the land to sink under the load. In some areas, this sinking created deep basins, some of which now lie far below sea level, hidden under km of ice. These basins can trap heat from the Earth's interior, helping to maintain subglacial lakes and influencing how ice flows above them. The interplay between drifting land, shifting climate, and growing ice created a complex evolving system. None of these factors acted alone. The position of the continent influenced the climate. The climate influenced the growth of ice. The ice influenced the shape and behavior of the land. As Antarctica settled more firmly into its polar position, the seasons took on a more extreme character. Summers became cooler and shorter. Winters grew longer and darker. The contrast between light and dark intensified with months of continuous daylight, followed by months of near total night. Life on the continent faced increasing challenges. Plants that once thrived along rivers and in valleys found their growing season shrinking. Animals that depended on those plants had to adapt, migrate, or disappear. The fossil record suggests that this process was not a sudden collapse, but a gradual retreat. Species persisted in favorable pockets, especially in coastal regions and lower latitudes, even as the interior grew colder. Over time, those pockets became smaller and more isolated until eventually the ice claimed almost everything. Yet even as Antarctica became increasingly frozen, the continent never truly stopped moving. The tectonic plate beneath it continues to shift even today. The changes are too small to notice without precise instruments, but they are real. Earthquakes occur in and around Antarctica, though most are far from human settlements. Volcanic activity persists in certain regions, most notably at Mount Erebus, an active volcano that rises above the ice on Ross Island. These events are reminders that the forces shaping the continent from below are still very much alive. There is also evidence that parts of the crust beneath Antarctica are warmer than others due to variations in heat flow from the mantle. These warm spots can influence how ice melts at the base of the ice sheet, creating areas of faster flow and shaping the overall behavior of the ice. In this way, the continent's deep, slow motion continues to interact with the more visible motion of ice and water at the surface. The story of Antarctica is not just written in ancient fossils and buried valleys, but in ongoing processes that are still unfolding. As you sit and imagine this immense, patient journey, it might help to think of the continent not as a single solid object, but as part of a much larger system. The same forces that moved Antarctica also moved Africa, Australia, South America, and every other piece of land on the planet. The world we know today is the result of all those movements layered on top of one another over immense spans of time. This perspective can make modern maps feel almost temporary. The outlines we see on a globe or a screen are just the current arrangement, a momentary snapshot in a long sequence. Given enough time, those shapes will change again. Oceans will widen or close. Continents will collide or drift apart. New mountains will rise. Old ones will wear down. Antarctica, in that sense, is both a destination and a waypoint. It arrived at the South Pole after a long journey, but it won't stay there forever. In tens or hundreds of millions of years, the tectonic plates will rearrange themselves once more, and the southern continent will find itself in a new position under a different sky with a different relationship to the sun and the oceans. Of course, none of that is something any of us will witness. Our own sense of time is far too small to grasp movements measured in millions of years. But understanding that these motions exist can subtly change how we think about the world around us. The ground beneath your feet, wherever you are right now, is part of this same system. It is moving slowly, almost imperceptibly, carried along by the same deep forces that carried Antarctica into the cold. Somewhere far above the surface of Antarctica, far above the clouds, the winds, and even the thin edge of the atmosphere, the Earth is moving through space in a way that feels almost too simple to matter. It spins, it circles the sun, it leans just a little to one side. These motions happen whether anyone is watching or not, steady and reliable, like the background rhythm of the planet itself. Yet over long stretches of time, those gentle movements have the power to reshape entire continents, turning green landscapes into frozen deserts and back again. To understand how Antarctica's fate became so tightly bound to the sky, it helps to start with that slight lean, the tilt of the Earth's axis. Right now, the planet is tilted at about 23.5 degrees. That number doesn't usually come up in everyday conversation, but it's the reasons exist at all. Because of that tilt, different parts of the world receive different amounts of sunlight at different times of the year. When the northern half of the Earth is tilted toward the sun, it experiences summer. The southern half, tilted away, experiences winter. 6 months later, the roles reverse. The further you go from the equator, the more extreme this effect becomes. Near the poles, it leads to months of continuous daylight in summer and months of darkness in winter. Antarctica sits at the very end of that scale. Its relationship with the sun is always dramatic. Even in a warm world, the continent would have experienced these long cycles of light and dark. But the exact intensity of those cycles depends not just on where the continent sits, but on how the Earth itself is oriented in space. The tilt of the Earth is not fixed. It changes slowly over tens of thousands of years. Sometimes the planet leans a little more. Sometimes it straightens up a bit. These changes are small, usually shifting between about 22 degrees and 24.5 degrees, but their effects can be significant, especially in high-latitude regions like Antarctica. When the tilt is greater, the seasons become more extreme. Summers get warmer and winters get colder. When the tilt is smaller, the difference between seasons is less pronounced. Summers are cooler and winters are milder. For a place on the edge of freezing, those differences can determine whether snow melts away each year or builds up layer by layer. In Antarctica's past, as the continent drifted southward and the climate cooled, these subtle shifts in tilt became increasingly important. But tilt is only part of the story. The Earth's orbit around the Sun is not a perfect circle. It's slightly elliptical, meaning that at some points in the year the planet is a bit closer to the Sun, and at others it's a bit farther away. This shape also changes over time, cycling between more circular and more elliptical patterns over a period of about 100,000 years. When the orbit is more elliptical, the difference in distance between the closest and farthest points becomes larger. That can make seasons more intense in one hemisphere and milder in the other, depending on how the timing of the seasons lines up with those points in the orbit. Then there is a third motion, less obvious, but just as important. The Earth doesn't just spin and orbit. Its axis also wobbles slowly like a spinning top. This wobble, known as precession, changes the timing of the seasons relative to the planet's position in its orbit. Over a cycle of about 26,000 years, the dates when seasons begin gradually shift. These three movements, changes in tilt, changes in orbital shape, and the wobble of the axis, work together to alter how sunlight is distributed across the planet over long periods of time. They don't change the total amount of energy Earth receives from the Sun by much, but they do change where and when that energy arrives. In the early 20th century, a scientist named Milutin Milankovitch recognized that these cycles could help explain patterns of ice ages and warm periods seen in the geological record. His idea was that when conditions line up in certain ways, summers in high-latitude regions become cool enough that snow from the previous winter doesn't fully melt. Over time, that snow compacts into ice and glaciers grow. When conditions shift the other way, summers become warm enough to melt more snow and ice than accumulates in winter, causing ice sheets to retreat. Antarctica, with its extreme position at the bottom of the world, is especially sensitive to these changes. Small variations in the amount of sunlight it receives during summer can have large effects on how much ice builds up or melts away. To see how this plays out, it helps to imagine a simple scenario. Picture a winter in ancient Antarctica during a period when the climate is already trending cooler. Snow falls across the land, covering forests, hills, and valleys. When summer arrives, the sun returns, circling low in the sky for weeks on end. If the sunlight is strong enough and the temperatures rise high enough, much of that snow melts, feeding rivers and lakes and leaving the ground exposed again. But if, because of the Earth's orbital and tilt cycles, that summer sunlight is slightly weaker, the snow doesn't fully melt. Some of it remains through the summer and into the next winter. The following winter adds another layer. Over time, those layers compress, turning into ice. Once a patch of land becomes permanently ice-covered, it begins to change the local climate. Ice reflects a large portion of incoming sunlight back into space. This is known as the albedo effect. Dark surfaces like soil and vegetation absorb more sunlight and warm up. Bright surfaces like snow and ice reflect it. So as more of Antarctica's surface turned white, it absorbed less heat. This made it easier for ice to persist and spread, even if the underlying astronomical conditions shifted slightly toward warmth. The ice itself became part of the system, reinforcing the cooling trend. This feedback loop is one of the reasons ice sheets, once they reach a certain size, can be remarkably stable. They don't just respond to climate, they help shape it. In Antarctica's case, the planet's slow changes in tilt and orbit likely played a role in determining when and where ice first gained a permanent foothold. High mountain regions and plateaus, where temperatures were already lower, would have been the first to see year-round snow and ice. From there, glaciers would have flowed downhill, following the paths carved by ancient rivers spreading across valleys and plains. Each advance would have covered more of the dark heat absorbing ground with reflective ice, further tipping the balance. Over hundreds of thousands and millions of years, These processes turned patches of ice into regional ice sheets, and eventually into the vast continent-spanning ice cover we see today. What makes this story especially interesting is how these astronomical cycles interact with the other factors we've already explored. The movement of the continent itself placed Antarctica in a position where it was more vulnerable to cooling. The formation of the circumpolar current isolated it from warm ocean waters. And then the rhythms of the Earth's orbit and tilt provided the timing, the gentle push that nudged the system one way or the other. It's not a simple single-cause explanation. It's a layered process with each part influencing the others. You can think of it like a set of slow-moving dials. One dial represents the position of the continents. Another represents the composition of the atmosphere. Another represents the flow of the oceans. And another represents the Earth's motion through space. As those dials turn, sometimes independently, sometimes in sync, the climate of a place like Antarctica shifts. At certain times, the settings line up in a way that favors warmth and flowing water. At other times, they line up in a way that favors cold and ice. Evidence for the influence of these cycles can be found in the layers of ice itself. Ice cores drilled from the Antarctic ice sheet show regular patterns in temperature and atmospheric composition that match the timing of known changes in the Earth's orbit and tilt. These cores are like long frozen timelines. Each layer represents a year or a season of snowfall. Trapped within those layers are tiny bubbles of ancient air, preserving samples of the atmosphere from thousands and even hundreds of thousands of years ago. By analyzing the chemical makeup of the ice and the gases inside those bubbles, scientists can reconstruct past temperatures, carbon dioxide levels, and even patterns of wind and dust. When they compare these records to calculations of how the Earth's orbit and tilt have changed over time, they find strong correlations. This doesn't mean that orbital cycles are the only drivers of climate change. Far from it. Volcanic activity, changes in greenhouse gases, and shifts in ocean circulation all play major roles. But the orbital cycles provide a kind of packing, a background rhythm that helps set the timing of major transitions between colder and warmer periods. In Antarctica, this rhythm has been playing for a very long time. Even after the continent became fully glaciated, the ice sheet continued to expand and contract in response to these cycles. During colder periods, the ice grew thicker and spread farther toward the coast. During warmer interludes, it thinned and retreated. The difference between those states can be measured in meters of ice thickness and in kilometers of coastline. For a continent-sized ice sheet, even small changes add up to enormous volumes of frozen water. What's striking is how this slow cosmic scale motion connects to the small, everyday experiences of light and shadow. The length of a day, the angle of the sun in the sky, the changing seasons. These are things we notice without thinking about the larger mechanics behind them. For Antarctica, those same mechanics stretched over vast time scales have determined whether a given place is home to a forest, a river, or a glacier. It's also worth noting that these cycles don't operate in isolation from the living world. Plants and animals respond to changes in temperature and light. As conditions shift, ecosystems move, adapt, or disappear. Those biological changes can in turn influence the climate, for example, by altering how much carbon is stored in vegetation and soils. In the warmer periods of Antarctica's past, forests and wetlands would have played a role in regulating the local and global carbon cycle. As those ecosystems retreated and were replaced by ice, that role changed. Over long periods, these feedbacks become part of the broader system that determines how the planet responds to shifts in sunlight and orbital patterns. There is a subtle elegance to this interplay. The movement of a planet through space governed by gravity and inertia influences the growth of trees and the flow of rivers on a distant continent. The presence or absence of those trees and rivers then feeds back into the chemistry of the atmosphere, which affects how much heat the planet retains, which in turn influences how ice responds to the next cycle of tilt and orbit. All of this happens without intention or awareness. It's a system of cause and effect layered on top of itself over millions of years. As you imagine this, it might help to think about how slow these processes really are. A full cycle of the Earth's tilt takes about 41,000 years. Changes in orbital shape take around 100,000 years. The wobble of the axis cycles over about 26,000 years. These numbers are far beyond any human sense of time. They're long enough that entire civilizations can rise and fall without even a small fraction of a cycle completing. Yet over geological time scales, they become the steady heartbeat of the climate system. Antarctica's response to that heartbeat has been shaped by its position and its history. When the continent was warmer and greener, the cycles would have influenced the length and intensity of growing seasons, the amount of snow that fell in winter, and the availability of water in summer. As the continent cooled and ice began to dominate, those same cycles became the difference between ice advancing and retreating, between a glacier thickening and thinning. In the present day, these astronomical rhythms are still at work. The Earth's tilt, orbit, and wobble continue to change. The amount of sunlight reaching Antarctica in summer and winter continues to vary. But now these natural cycles are interacting with another powerful influence: the rapid increase in greenhouse gases caused by human activity. This doesn't replace the orbital cycles. It adds a new layer on top of them, altering the baseline conditions under which they operate. Understanding how Antarctica responded to past changes in sunlight and temperature can help scientists better predict how it might respond to the combined effects of natural cycles and modern warming. For now, though, it's enough to recognize that the fate of a continent can be shaped by something as simple and as vast as the way a planet leans toward its star. As the Earth continued its slow, graceful motions through space, Antarctica's surface responded in ways that were both subtle and dramatic. Snow lingered a little longer here. Ice thickened a little more there. Over time, these small differences grew into sweeping changes. The green landscapes of the past gradually gave way to a world dominated by white and blue, but ice that stretched from the high interior to the edge of the sea. The sun still circled the sky in summer and disappeared in winter, but its warmth no longer reached the ground in the same way. If you stand on the edge of Antarctica today at one of the rare places where rock meets open water, the ocean does not feel like a quiet neighbor. It feels alive, restless, always in motion. Waves crash against ice cliffs. Winds sweep across the surface, pushing water into long, rolling swells. Beneath that surface, unseen and powerful, currents move vast amounts of heat and cold around the planet. It is easy to think of the ice as the defining feature of this continent. But in many ways, it is the water that surrounds it that truly decided its fate. To understand how the ocean became such a powerful influence, it helps to think of the planet as a system of connected loops. Heat from the sun warms the surface of the Earth, but it doesn't stay in one place. Air and water move it around, carrying warmth from the equator toward the poles and cold back toward the tropics. Without this constant exchange, the world would be far more extreme, with scorching heat near the middle and deep, unbroken cold at the edges. For a long time in Earth's history, Antarctica was part of that global exchange in a relatively balanced way. When it was still connected to other southern continents, warm ocean water could reach its shores. Currents flowed southward along coastlines, carrying heat from lower latitudes into the high southern regions. The ocean acted like a conveyor belt, smoothing out temperature differences and helping maintain a climate that, while cool and seasonal, was not locked into permanent ice. This balance began to change as the continents continued their slow separation. When South America finally pulled away from Antarctica, a narrow gap opened between them. Over time, that gap widened into a deep ocean passage, now known as the Drake Passage. Around the same period, Australia completed its separation from the eastern side of Antarctica. These two openings, one to the west and one to the east, created something entirely new in the global ocean system. For the first time, there was a continuous ring of open water that could flow all the way around the southern continent without being blocked by land. This might sound like a small geographic detail, just another feature on a map, but in terms of how the planet moves heat, it was a major shift. Once that ring of water existed, strong winds that circle the southern hemisphere were able to drive a powerful current around Antarctica. This current, which we now call the Antarctic Circumpolar Current, is unlike any other on Earth. It doesn't run along a coastline or between continents. It circles the globe uninterrupted, linking the Atlantic, Pacific, and Indian Oceans into a single flowing system. The scale of this current is hard to overstate. It is the largest ocean current on the planet, carrying more water than all the world's rivers combined. It moves hundreds of millions of cubic meters of water every second, creating a continuous band of motion that encircles the continent. What makes this current so important for Antarctica's climate is not just how much water it moves, but what kind of water it moves. The Antarctic Circumpolar Current acts as a barrier, a kind of liquid wall that separates the cold southern ocean from the warmer waters farther north. Before this current formed, warm water from lower latitudes could more easily reach the Antarctic coast. After it formed, that warm water was largely deflected away, trapped on the other side of the circulating flow. The water that remained near Antarctica grew colder, influenced more by the polar atmosphere and less by heat from the tropics. This change in ocean circulation had a cascading effect on the climate of the entire region. Colder ocean water means colder air above it. Colder air holds less moisture. Snow that falls is less likely to melt in summer. Ice begins to persist and spread. In this way, the ocean didn't just respond to Antarctica's cooling. It actively helped drive it. The formation of the circumpolar current also changed how deep water moved around the globe. In the modern ocean, cold, dense water forms near Antarctica when surface water cools and becomes heavy enough to sink. This sinking water then flows northward along the ocean floor, eventually rising in other parts of the world. This process is a key part of what scientists call the global overturning circulation, sometimes described as the ocean's conveyor belt. It plays a major role in regulating climate by moving heat and nutrients around the planet. As Antarctica became colder and more ice-covered, this process intensified. The cold, salty water formed near the continent became a major source of deep ocean currents that influenced conditions as far away as the North Atlantic and the Pacific. So, in a sense, the freezing of Antarctica didn't just change the southernmost part of the world. It altered the behavior of the oceans everywhere. Closer to the continent, the interaction between ice and ocean created another layer of complexity. As glaciers flowed outward and reached the sea, they began to form floating extensions known as ice shelves. These shelves are thick slabs of ice that remain attached to the land, but float on the ocean's surface. Ice shelves act like braces for the glaciers behind them. They slow the flow of ice from the interior into the ocean, helping stabilize the ice sheet. The ocean, however, has a way of working around this barrier. Warm water, even slightly warm by polar standards, can circulate beneath these shelves. When it does, it melts the ice from below. This thinning weakens the shelves, making them more likely to crack or break apart. In the ancient past, as the ocean around Antarctica cooled overall, the balance between ice growth and melting shifted. Colder surface waters meant less melting at the edges of glaciers. More ice was able to reach the coast and form shelves. These shelves in turn helped the ice sheet grow thicker and more stable. But the ocean was never a passive player. Changes in wind patterns driven by shifts in the planet's climate and atmospheric circulation could alter how much relatively warm water reached the underside of the ice. These variations could speed up or slow down the growth of the ice sheet over long periods. This push and pull between ice and ocean created a dynamic system, one that responded to both local conditions and global changes. To see how deeply the ocean influenced Antarctica's transformation, it helps to look at the timing of events in the geological record. Evidence from sediments, fossils, and chemical signatures suggest that the major expansion of the Antarctic ice sheet occurred around 34 million years ago at the boundary between the Eocene and Oligocene epochs. This timing lines up closely with the final opening of the Drake Passage and the strengthening of the circumpolar current. It also coincides with a significant drop in global carbon dioxide levels, which would have contributed to overall cooling. The combination of these factors created a tipping point. The continent was already drifting southward. The atmosphere was holding less heat, and now the ocean currents were cutting off one of the last major sources of warmth. Once that threshold was crossed, ice sheets grew rapidly. Within a relatively short geological period, Antarctica shifted from a patchwork of glaciers and ice-free regions to a continent dominated by ice. From that point on, the ocean helped maintain this frozen state. The circumpolar current continued to isolate Antarctica from warmer waters. Cold, dense water formed around the continent and sank, reinforcing global circulation patterns that kept the Southern Ocean cold. The ice sheet itself became a major influence on the ocean. As ice formed and melted, it changed the salinity of the surrounding water. When ice forms, it leaves behind salt, making the nearby water denser. When ice melts, it adds fresh water, making the surface layer less salty and lighter. These changes can affect how water layers stack and mix, influencing everything from nutrient distribution to the formation of deep currents. This interplay between ice and ocean created a feedback loop that helped lock Antarctica into its role as the cold pole of the planet. Yet, even in this frozen state, the ocean continued to shape the hidden landscape beneath the ice. Subglacial water, often fed by geothermal heat and pressure melting at the base of the ice sheet, can flow along channels that ultimately connect to the sea. In some regions, this water emerges the grounding line, the point where the ice sheet lifts off the land and begins to float as an ice shelf. There it mixes with seawater, affecting local circulation and melting patterns. The presence of this fresh water can create layers in the ocean with lighter, fresher water sitting on top of denser, saltier water. This layering can influence how heat is transferred from the deeper ocean to the ice shelves above. In ancient Antarctica, before the ice sheet became dominant, similar interactions would have occurred in a different form. Rivers would have carried fresh water into coastal seas, creating estuaries and zones of mixing. These areas are often among the most biologically productive in the world, rich in nutrients and life. As the continent cooled and ice replaced rivers, the nature of this freshwater input changed, but the connection between land and sea remained. There is also a broader planetary perspective to consider. The formation of the circumpolar current didn't just affect Antarctica. By linking the world's major ocean basins, it changed how heat and nutrients moved globally. Some scientists believe this reorganization of ocean circulation played a role in cooling the entire planet, not just the southern regions. By altering how heat was distributed between the hemispheres and how carbon was stored in the deep ocean, the new current system may have contributed to a general trend toward cooler global climates. This means that Antarctica's freezing may have been both a cause and a consequence of wider changes in the Earth system. The continent and the ocean influenced each other in a complex dance, each shaping the other over millions of years. As you imagine this, it can be helpful to picture the ocean not as a static body of water, but as a moving three-dimensional structure. There are surface currents driven by wind. There are deep currents driven by differences in temperature and salinity. There are swirling eddies, upwellings, and downwellings, all interacting in a constantly shifting pattern. Around Antarctica, this pattern takes on a distinctive character. The strong winds of the southern hemisphere drive surface waters eastward. The cold, dense water formed near the ice sinks and spreads northward along the ocean floor. Warmer, lighter water from lower latitudes tries to push southward, but is largely kept at bay by the circulating current. This creates a kind of thermal moat around the continent, one that has persisted for tens of millions of years. The stability of this system has helped to keep Antarctica cold, even during periods when the rest of the world experienced warmer climates. While ice sheets in the northern hemisphere have advanced and retreated dramatically over the past few million years, the core of the Antarctic ice sheet has remained in place. That doesn't mean it has been completely unchanged. The edges of the ice sheet have shifted back and forth in response to climate variations. Ice shelves have grown and collapsed. Glaciers have sped up and slowed down, but the presence of the circumpolar current has made Antarctica more resistant to warming than it might otherwise have been. In more recent times, however, this balance has shown signs of strain. Changes in wind patterns and ocean temperatures have allowed warmer water to reach some parts of the Antarctic coast more easily, particularly in the west. This has led to increased melting of ice shelves from below, weakening them and allowing glaciers behind them to flow more rapidly into the ocean. These processes are part of the modern story of Antarctica, one that scientists are watching closely because of its implications for global sea levels. Looking back into the deeper past, though the ocean's role in sealing Antarctica's fate stands out as a powerful example of how interconnected the Earth system is. A shift in the position of a continent opens a new ocean passage. That passage allows a current to form. That current changes how heat is distributed. That change helps turn a green land into a frozen one. None of these steps happens in isolation. Each depends on the others. The result is a transformation that feels almost inevitable in hindsight, even though it was the product of many small, slow changes. As you sit with this idea, it might be interesting to think about how often we overlook the role of the ocean in shaping the world we see. We notice mountains, rivers, forests, and ice because they are solid and visible. The ocean covering most of the planet can feel like a backdrop rather than an active participant. But in the story of Antarctica, the water surrounding the continent was not just a setting. It was a driver, a gatekeeper that controlled the flow of warmth and cold, a force that helped decide whether trees could grow or ice would take their place. And even now, in the present, the ocean continues to hold that role. The currents still circle. The deep water still forms and sinks. The balance between ice and sea still shifts, sometimes subtly, sometimes in ways that ripple across the entire planet. Long before the wind learned how to whistle across empty ice, and before the ground forgot what it felt like to be soft underfoot, the southern land was not silent. It was a place with movement, sound, and the steady presence of living things going about their days in a world that to them was simply home. The idea of animals and complex ecosystems thriving in what we now call Antarctica can feel almost like a trick of the imagination. But the land itself carries the evidence. Tucked into layers of rock, fragments of bone, and subtle chemical traces that speak of a time when life found plenty of room to grow at the bottom of the world. To understand what kinds of creatures lived there, it helps to let go of the modern picture of Antarctica as an isolated extreme environment. During the warmer periods of its past, the continent was part of a network of southern lands that shared plants, animals, and climate patterns. There were no vast frozen barriers separating it from the rest of the world. Instead, there were land bridges, shallow seas, and coastlines that allowed species to move, spread, and adapt. The most famous of these ancient residents are dinosaurs. Their presence in Antarctica often surprises people, partly because we tend to imagine dinosaurs in lush tropical settings. Yet the fossil record shows that these animals were remarkably adaptable, living in a wide range of environments from deserts to forests, from low latitudes to high. In Antarctica, dinosaur fossils have been found on the Antarctic Peninsula and in the trans-Antarctic mountains, areas that were once closer to the continent's ancient coastlines. These remains include bones from plant-eating dinosaurs that would have roamed the forests and flood plains, feeding on leaves, shoots, and other vegetation. One such dinosaur is Antarct, a name that literally means Antarctic shield. It was a type of armored dinosaur covered in bony plates that offered protection from predators. Its fossils suggest an animal that moved through low vegetation, likely browsing on plants close to the ground. There is also evidence of larger herbivores, including long-necked sauropod dinosaurs in earlier periods and more compact beaked dinosaurs later on. These animals would have required significant amounts of food, which in turn implies the presence of extensive plant life to support them. Predators would have followed. While their fossils are rarer, likely because of the way bones are preserved and discovered, there is evidence that meat dinosaurs lived in the region as well. These would have hunted the herbivores or scavenged from their remains, forming the top tier of the local food web. Living in a high-latitude environment would have posed unique challenges for these animals, even in a warm climate. The long periods of darkness during winter would have limited plant growth and potentially reduced the availability of food. How did dinosaurs cope with that? One possibility is migration. Some species may have moved northward during the darkest months following the sun and the vegetation, then returned south when summer brought continuous daylight and a burst of plant growth. Another possibility is that they adapted to seasonal scarcity. Modern animals in temperate and polar regions often build up fat reserves during times of plenty, then rely on those reserves when food becomes scarce. Dinosaurs, being warm-blooded, or at least partially warm-blooded, may have used similar strategies. There is also the intriguing idea that some dinosaurs might have had feathers or feather-like structures that helped them retain heat. Fossils from other parts of the world show that many dinosaurs, even large ones, had some form of insulation. In a place with cool temperatures and long winters, this would have been especially useful. Beyond dinosaurs, the ancient Antarctic ecosystem included a wide range of other animals. Early mammals, for example, were already present during the time when dinosaurs still ruled the land. These mammals were generally small, often no larger than modern rodents, and they likely lived in the undergrowth, feeding on insects, seeds, and other small food sources. Fossil teeth and jaw fragments from these mammals have been found in Antarctic rock, providing clues about their diets and lifestyles. Some appear to have been generalists, able to eat a variety of foods, which would have been an advantage in an environment with strong seasonal changes. There were also reptiles and amphibians. Fossils of ancient amphibians suggest the presence of freshwater habitats like rivers, lakes, and wetlands. Amphibians depend on water for reproduction and often have sensitive skin that requires moist conditions. So their presence supports the idea of a relatively wet, mild climate. Birds, too, were part of this ancient world. Early relatives of modern birds lived alongside dinosaurs. And after the dinosaurs went extinct, birds became even more prominent. Fossils of large, flightless birds and early flying species have been found in Antarctica, indicating that the continent continued to support complex animal life even as the climate began to cool. One particularly fascinating group of animals that later made Antarctica their home are penguins. Today, penguins are almost synonymous with the frozen South, but their ancestors lived in a much warmer world. Fossil penguins found in Antarctic and nearby regions date back to around 60 million years ago, not long after the extinction of the dinosaurs. These early penguins were often much larger than the species we see today, some standing well over a meter tall. They lived along coastlines and in shallow seas, diving for fish and other marine life. The presence of these large penguins suggests that the surrounding waters were productive, rich in food, and not yet dominated by the extreme cold that characterizes the modern Southern Ocean. Marine life in general was a major part of Antarctica's ancient ecosystem. The shallow seas around the continent supported a variety of fish, mollusks, and other invertebrates. Fossil shells, bones, and even impressions of soft-body creatures have been found in sedimentary rocks that were once part of the ocean floor. These marine ecosystems would have been closely linked to what happened on land. Rivers carried nutrients from the forests and soils into the sea, supporting plankton growth, which in turn fed larger organisms. This land connection is a hallmark of productive coastal environments. As the climate cooled and ice began to advance, these connections changed. Rivers froze or were buried. Sediment and nutrient flow patterns shifted. The composition of marine life evolved in response to colder, more stable conditions. But before that transformation took hold, Antarctica was part of a lively network of ecosystems that extended across land and sea. One of the most compelling aspects of studying these ancient creatures is the way their remains link Antarctica to other parts of the world. Fossils of similar species have been found in South America, Australia, and Africa, reflecting the shared history of these continents as parts of Gondwana. For example, certain groups of plants and animals appear in both Antarctica and Australia during the same geological periods. This suggests that they were able to move freely between the two when the land masses were still connected. These connections help scientists reconstruct not just the positions of the continents, but the pathways that life used to spread and diversify. They reveal a world where the boundaries we now take for granted did not yet exist. As conditions in Antarctica grew harsher, the animals that lived there faced increasing pressure. Some species likely adapted to the cold, changing their behavior, diet, or physiology. Others may have migrated northward, following more favorable conditions as the ice advanced. For many, however, the changes were simply too great. The expansion of ice sheets would have reduced available habitat, shrinking forests and wetlands into isolated patches. Food sources would have become scarcer and more seasonal. Eventually, large areas of the continent would have become uninhabitable for land animals. The fossil record reflects this gradual decline. In younger rock layers, the diversity of land animal fossils decreases. Marine fossils continue to appear, reflecting the fact that the ocean remained a viable habitat even as the land froze over. Penguins and seals, for example, became well adapted to the cold waters of the Southern Ocean, thriving in an environment that would have been deadly to most terrestrial animals. The story of these creatures is not just one of loss, though. It is also a story of resilience and adaptation. Life did not vanish from the region. It changed. Marine ecosystems became the dominant form of life around Antarctica. On land, life retreated to the edges, surviving in tiny niches where conditions allowed, such as in coastal areas, geothermal sites, or much later in the form of hardy microorganisms living in and on the ice. Even today, Antarctica is not truly lifeless. Microbes live in the snow, in subglacial lakes, and in the cold, dry valleys where almost no ice accumulates. Mosses and lichens grow in sheltered spots along the coast. In the surrounding seas, life is abundant. From tiny plankton to whales, these modern ecosystems are in a way the descendants of the ancient ones. They're shaped by the same forces of climate, geography, and ocean circulation, just under very different conditions. One of the most intriguing questions scientists continue to explore is how quickly and in what ways these ancient animals responded to the changing climate. Did some species manage to survive in isolated refuges for long periods as the ice advanced? Were there sudden tipping points where ecosystems collapsed? Or was the process so gradual that life simply flowed away, following the shifting boundaries of suitable habitat. To answer these questions, researchers study not just bones and shells, but also subtle markers in the rock. Changes in the types of pollen found in sediments can indicate shifts in vegetation. Variations in isotopic ratios can point to changes in temperature and water sources. Together, these clues help build a timeline of how ecosystems evolved as the continent cooled. This kind of work requires patience. Field seasons in Antarctica are short. The weather is unpredictable. Many fossil sites are remote and difficult to reach. When scientists do manage to collect samples, the analysis can take years. Yet the results have steadily transformed our understanding of the continent. Each new fossil discovery adds another piece to the picture, showing that Antarctica's past was far more biologically rich than its present. As you imagine these ancient creatures, it might help to think of them not as isolated curiosities, but as parts of a living system that once functioned much like ecosystems elsewhere in the world. There were predators and prey, plants and pollinators, scavengers and decomposers. There were seasonal rhythms, migrations and life cycles shaped by the rise and fall of the sun. The difference is not in the basic structure of the system, but in the setting. A place we now associate with extreme cold and emptiness was once a stage for the same kinds of interactions that play out in forests, wetlands, and coastlines around the globe today. There is something quietly powerful about that realization. It suggests that the conditions we see in any given place are not permanent. They are chapters in a longer story written by the slow movement of land, water, air, and life itself. In Antarctica, the chapter of animals roaming through forests and along rivers eventually gave way to a chapter of ice and ocean-dominated ecosystems. The transition was shaped by the same forces we've been following. The drifting of continents, the rhythms of the planet's orbit, and the circulation of the oceans. As those forces continued to work, the land-based creatures of the South either left or vanished, while marine life took center stage in the cold, nutrient-rich waters that formed around the frozen continent. Looking ahead, the story does not end there. The traces left by those ancient animals in bone, in rock, and in the genetic relationships of modern species continue to inform how scientists think about evolution, climate change, and the resilience of life. They also invite a more personal kind of reflection. The idea that a place so distant and inhospitable today was once home to forests, rivers, and roaming animals can shift how we think about the world as a whole. It highlights the deep, ongoing connection between life and the planet that supports it. There is a point in every long transformation where the change becomes hard to ignore. Not a single day, not a dramatic instant where everything flips from one state to another, but a threshold, a gradual crossing where the old world can no longer quite hold on, and the new one begins to shape the rules. For Antarctica, that threshold came when snow stopped being a seasonal visitor and started to become a permanent resident. For millions of years, the land had lived with winter and summer in a familiar rhythm. Snow fell in the colder months. In the warmer months, much of it melted away. Rivers swelled with runoff. Forest breathed in the long daylight of summer and rested in the long darkness of winter. Even as the climate cooled and the continent drifted farther south, that cycle persisted in many regions. The balance was delicate, but it held. Then, little by little, it didn't. To understand how ice took over the land, it helps to imagine the process not as a sweeping wall of white advancing across the continent, but as a collection of small, scattered beginnings. The first places where ice gained a permanent foothold were likely the high points. Mountain ridges, plateaus, and elevated basins where temperatures were already lower, and winds could pile up snow in thick drifts. In these places, summer warmth became just a little less effective. A patch of snow survived through the season. The next winter added another layer. Over time, the weight of those layers compressed the snow beneath into a denser, granular form called firn, and eventually into solid ice. Once that happened, the surface changed in a way that mattered for everything that followed. Ice reflects much more sunlight than soil, rock, or vegetation. Where the land had once absorbed the sun's energy and warmed up, it now bounced a large portion of that energy back into the sky. This made the local climate colder. Colder air meant less melting in summer. Less melting meant more snow, and ice could accumulate. It was a feedback loop that fed on itself, slow but steady, nudging those first patches of permanent ice outward. At the same time, the broader climate system was shifting. Carbon dioxide levels in the atmosphere were lower than they had been during Antarctica's warmest periods. The ocean currents around the continent had reorganized, limiting the flow of warmth from lower latitudes. The Earth's orbital rhythms were delivering patterns of sunlight that in certain cycles favored cooler summers. All of these factors worked together, creating conditions where the balance tipped more often toward accumulation than melting. In the early stages, the ice didn't cover everything. It grew in pockets. A glacier formed in a mountain valley, following the same path a river had once taken. Another spread across a high plateau, creeping outward along gentle slopes. These glaciers moved slowly, driven by the weight of their own mass, flowing like incredibly thick, cold honey. As they moved, they reshaped the land beneath them. Rock was scraped and polished. Loose sediment was picked up and carried along. Valleys were widened and smoothed. In places where ice flowed over softer rock, it carved deeper channels, reinforcing the pathways that water had once created. For the forests and animals that still clung to parts of the continent, this would have been a gradual but relentless pressure. A valley that had supported trees and wetlands for thousands of years might find its growing season shrinking. A glacier advancing from the high ground could begin to encroach on the edges of the forest, covering soil and roots under a growing blanket of ice. Plants closest to the ice would struggle first. Shorter summers mean less time to grow and reproduce. Colder temperatures can damage tissues and limit the availability of liquid water in the soil. Over time, the forest would retreat, leaving behind patches of grass, shrubs, or bare ground. Animals dependent on those plants would follow. Herbivores might shift their feeding grounds downslope or toward the coast. Predators would track their prey. Species that could move would do so. Those that could not would face a narrowing set of options. In some regions, this process may have taken tens or hundreds of thousands of years. In others, where conditions were already close to the edge, it might have happened more quickly. One of the most significant moments in this long story came around 34 million years ago at the transition between the Eocene and Oligocene epochs. Geological records from around the world show evidence of a substantial global cooling event at this time in Antarctica. This cooling coincides with the rapid expansion of ice across much of the continent. Sediment cores drilled from the ocean floor near Antarctica reveal a sudden increase in ice-rafted debris around this period. These are bits of rock and sediment that were carried out to sea by glaciers and dropped as the ice melted. Their appearance in large quantities suggests that significant ice sheets had formed on land and were reaching the ocean. This doesn't mean that Antarctica instantly became the frozen giant we know today. The initial ice sheets were likely smaller and more dynamic, advancing and retreating in response to climate fluctuations. But it does mark a point where ice became a dominant feature of the landscape rather than a seasonal or regional one. As ice sheets grew, they began to influence the continent on a much larger scale. The weight of kiln of ice pressed down on the crust beneath, causing it to sink. This process, known as isostatic adjustment, reshaped the land, creating deep basins and altering drainage patterns. In some places, the sinking land allowed ice to thicken even more, creating a positive feedback loop. The lower the land sank, the colder it became because lower elevations at high latitudes often experienced lower temperatures. This made it easier for ice to persist and grow. The interaction between ice and ocean also became more pronounced. As glaciers reached the coast, they flowed out onto the sea, forming ice shelves. These floating extensions of the ice sheet changed the shape of the coastline and influenced how the ocean moved near the continent. Cold, dense water formed as ice grew and expelled salt into the surrounding sea. This water sank and spread northward along the ocean floor, becoming part of the global circulation system. The ocean, in turn, influenced how much heat reached the ice shells from below. This dance between ice and water created a system that was both powerful and sensitive. Small changes in temperature or circulation could lead to shifts in where and how quickly ice grew or melted. On land, the transformation was just as profound. The ancient river systems that had once carved the landscape became buried under ice. Some of them continued to influence the movement of ice and water beneath the surface, guiding subglacial flows. Others were sealed away, their paths preserved in the rock, waiting to be rediscovered millions of years later by radar and drilling. Soils that had built up over long periods of plant growth were scraped away or covered. Organic material, once part of a living ecosystem, became trapped in sediment layers or carried out to sea by glaciers. For the living world, this was a narrowing of possibilities. Forests became patches. Patches became isolated refugees. Eventually, even those refugees disappeared, except perhaps in the mildest coastal regions or areas influenced by geothermal heat. The fossil record suggests that by the time the main ice sheets were firmly established, most land animals had left or gone extinct in Antarctica. The land-based ecosystems that once thrived there were replaced by a landscape dominated by ice, wind, and rock. Yet the transition was not a clean break. There were long periods of fluctuation. Ice would advance during colder phases, then retreat during warmer ones. Coastlines would shift back and forth. Glaciers would grow and shrink, leaving behind layers of sediment that recorded their movements. These fluctuations are preserved in the geological record as alternating layers of different types of rock and sediment. Some layers reflect conditions dominated by ice with coarse debris and signs of glacial erosion. Others reflect more open ice-free conditions with finer sediments and traces of biological activity. By studying these layers, scientists can reconstruct a detailed timeline of how Antarctica's ice cover evolved. They can see when major advances occurred, when retreats happened, and how these changes lined up with shifts in global climate and atmospheric composition. One of the striking features of this timeline is how quickly things can change once certain thresholds are crossed. For long periods, the system might hover near a balance point with ice growing in some areas and shrinking in others. Then a relatively small change, a drop in carbon dioxide, a shift in ocean circulation, a change in summer sunlight can push the system into a new state. In Antarctica's case, once the ice sheets reached a certain size, they became much harder to dislodge. The reflective surface, the altered ocean circulation, and the changed land elevation all work together to stabilize the frozen condition. This doesn't mean the ice became completely immune to change. Over the past few million years, the edges of the Antarctic ice sheet have advanced and retreated many times, especially in response to the ice ages that affected the northern hemisphere. But the core of the ice sheet, particularly in East Antarctica, has remained largely intact. From a human perspective, it can be difficult to grasp what it means for a landscape to be reshaped over millions of years. We're used to thinking in terms of seasons, years, and lifetimes. The moment ice took over the land was not something any living creature would have experienced as a single dramatic event. Instead, it would have felt like a slow tightening of the world. Summers growing a little shorter, winters lingering a little longer, Snow patches that used to melt now staying through the warm months. Glaciers that used to stop in the high valleys now reaching farther down toward the plains. For a forest, that might mean a line of trees dying back year by year, leaving open ground behind. For an animal, it might mean traveling farther each season to find food, or finding that familiar habitats have changed beyond recognition. There is a quiet, almost invisible quality to this kind of transformation. It doesn't announce itself. It just keeps going, guided by forces far larger and slower than any individual life. The land itself carries the memory of that shift. In some parts of Antarctica, beneath the ice, there are layers of sediment that mark the last days of open water and plant growth. Above them, there are layers dominated by glacial debris. The boundary between those layers is a physical record of the moment when ice became the main sculpture of the landscape. In other places, the story is written in the shape of the land. A valley that was once cut by a river now has the smooth, rounded profile of glacial erosion. A basin that once held a lake is now filled with ice and subglacial water. The presence of these features reminds us that the frozen world we see today is built on top of an older one. The ice did not erase the past. It covered it, preserved parts of it, and incorporated it into a new phase of the continent's history. As the ice sheets grew, they also began to influence the global climate in more direct ways. Large ice masses affect how the planet reflects sunlight. They influence atmospheric circulation patterns. They change the way the ocean stores and releases heat. The growth of the Antarctic ice sheet likely contributed to the cooling of the entire planet, not just the southern regions. By increasing the overall reflectivity of the Earth and altering ocean currents, it may have helped push the world toward the cooler conditions that eventually led to the ice ages in the northern hemisphere. This means that the moment ice took over the land in Antarctica was not just a local event. It was part of a broader shift in how the Earth system functioned. From a wider perspective, this transformation highlights how interconnected the planet is. A change in atmospheric composition, driven by processes happening across the globe, affects the temperature of a continent. The position of that continent influences ocean currents. Those currents affect climate patterns elsewhere. In this web of connections, the growth of ice in Antarctica becomes both a result and a cause, a response to changes and a driver of further change. As you reflect on this, it might be interesting to consider how different the world would look today if that tipping point had never been crossed. If Antarctica had remained warm enough to support forests and rivers, sea levels would be higher. Ocean circulation would be different. Climate patterns across the globe would likely have taken a very different path. The frozen continent we know today is in that sense a product of a particular set of circumstances that happened to align in a certain way millions of years ago. The ice itself continues to move even now. It flows slowly toward the sea, carrying with it bits of the land beneath. It calms and accelerates in response to changes in temperature and snowfall. It responds to the pull of gravity and the shape of the ground below. This motion is a reminder that even in a landscape dominated by ice, nothing is truly static. The moment ice took over the land did not mark the end of change. It marked the beginning of a new phase, one with its own rhythms and dynamics. There is a quiet irony in the way Antarctica tells its story. The very thing that transformed it into a frozen world also became one of the most detailed record keepers the planet has ever produced. The ice that buried forests, rivers, and ancient soils did not simply erase what came before. It sealed parts of the past away layer by layer, preserving a timeline that can be read with the right tools and a great deal of patience. To understand how this works, it helps to think about snowfall in a slightly different way. In most places, snow is a temporary visitor. It falls, it melts, it becomes part of the everyday cycle of water moving through the environment. In Antarctica's interior, Especially after the ice sheets became well established, snow began to behave differently. It fell and then it stayed. Each year, a thin layer of snow settled on the surface of the ice. The following year, another layer fell on top of it. Over time, the weight of the accumulating snow compressed the layers beneath, squeezing out air spaces and turning the fluffy crystals into dense ice. This process is slow, but it is steady. The result is a stack of layers, one on top of another, reaching back tens of thousands, hundreds of thousands, and in some places more than 1,000,000 years. These layers are not identical. The conditions under which the snow fell, the temperature of the air, the amount of dust in the atmosphere, even distant volcanic eruptions, all leave subtle marks in the ice. Tiny differences in color, texture, and chemical composition create a kind of barcode that scientists can read. To access this frozen record, researchers drill deep into the ice sheet, extracting long cylindrical cores. These cores can be several meters long, and when stacked end to end, they form a continuous column of ice that represents a slice through time. Holding one of these cores is like holding a physical timeline. The ice near the top represents recent years or decades. The ice deeper down represents a world that existed long before modern humans, before agriculture, before even the last ice age. One of the most remarkable things found in these cores is air. Not air in the sense of empty space, but actual samples of ancient atmosphere trapped in tiny bubbles. As snow compresses into ice, small pockets of air get sealed inside. These bubbles preserve the composition of the atmosphere at the moment the snow fell. By carefully breaking open these bubbles and analyzing the gases inside, scientists can measure past levels of carbon dioxide, methane, and other important components of the atmosphere. This allows them to see how greenhouse gas concentrations have changed over time, and how those checkers relate to shifts in temperature and climate. What they have found is a strong connection. Periods with higher levels of carbon dioxide and methane tend to line up with warmer temperatures. Periods with lower levels align with colder conditions and expanded ice. This relationship doesn't just appear once. It repeats cycle after cycle across hundreds of thousands of years. The ice cores show a rhythm of glacial and interglacial periods. Cold phases where ice expands and warmer phases where it retreats. In Antarctica, this rhythm is influenced by the orbital cycles of the Earth, the slow changes in tilt, orbit shape, and axial wobble that affect how sunlight is distributed across the planet. But the ice cores reveal that the atmosphere plays a crucial role in amplifying those changes. A small shift in sunlight can start a cooling or warming trend. Changes in greenhouse gases can then strengthen that trend, pushing the system toward a new state. Beyond gases, the ice also captures tiny particles from the world beyond Antarctica. Dust carried by winds from distant continents settles onto the snow. Ash from volcanic eruptions falls from the sky. Even traces of sea salt from ocean spray can make their way hundreds of kilometers inland. These particles become part of the ice layer where they land, creating a chemical fingerprint of the conditions at the time. By measuring the amount and type of dust in each layer, scientists can infer things about wind patterns, dryness in distant regions, and the extent of ice cover elsewhere in the world. For example, during colder, drier periods, more dust tends to be present in the atmosphere. Stronger winds and less vegetation in some regions allow more soil to be picked up and carried long distances. Ice layers from these times often contain higher concentrations of dust. During warmer, wetter periods, vegetation in many parts of the world helps hold soil in place, reducing the amount of dust in the air. Ice layers from these times tend to be cleaner. Volcanic eruptions leave another kind of marker. When a volcano erupts, it can send ash and sulfur compounds high into the atmosphere. These materials can travel around the globe before settling back to the surface. In the ice cores, These events often appear as thin, distinct layers rich in certain chemicals, such as sulfate. By matching these layers with known volcanic eruptions from other records, scientists can create precise timelines and even date the ice layers with remarkable accuracy. This ability to tie ice layers to specific events helps anchor the entire record in time. It turns the ice from a relative timeline into an absolute one where years and even seasons can be counted and compared. The frozen record doesn't just tell us about the atmosphere and distant events. It also holds clues about what was happening closer to the surface of the ice. Chemical signatures in the ice can reveal information about ocean conditions, such as the extent of sea ice and the productivity of marine ecosystems. For example, certain compounds produced by marine organisms can be carried into the atmosphere and deposited onto the ice. Changes in the concentration of these compounds over time can indicate shifts in ocean biology and sea ice cover. This creates a link between the frozen interior of Antarctica and the surrounding seas, showing how changes in one part of the system are reflected in another. There is also information about temperature itself locked into the ice. Water molecules come in slightly different forms called isotopes, depending on the number of neutrons in their atoms. The ratio of these isotopes in snow depends on the temperature at which the water vapor condensed and fell as snow. By measuring these ratios in each layer of ice, scientists can estimate past temperatures. This doesn't give an exact thermometer reading, but it provides a reliable way to track relative changes over time. When these temperature estimates are plotted alongside the greenhouse gas measurements from the air bubbles, a clear pattern emerges. They rise and fall together, reinforcing the idea that the atmosphere and the climate are closely linked. The deeper you go into the ice, the further back in time you travel. In East Antarctica, some of the deepest cores reach back more than 800,000 years. In a few locations, scientists believe the ice may be more than 1 million years old. That means there are parts of the Antarctic ice sheet that began forming long before modern humans appeared. They preserve a record of climates that existed in a world populated by early human ancestors. And even earlier. This depth of time gives the Antarctic ice a unique role in climate science. Other records such as tree rings or sediment cores from lakes and oceans are incredibly valuable, but they often cover shorter periods or have gaps. The ice cores provide a continuous high-resolution record that spans multiple glacial cycles. They allow scientists to see not just broad trends, but fine details. How quickly temperatures changed, how rapidly greenhouse gas levels rose or fell, and how the system responded to different kinds of disturbances. One of the insights that has emerged from this work is the idea of thresholds. The climate system does not always change smoothly and gradually. There are times when it appears to shift more abruptly, moving from one state to another over relatively short periods. In the ice cores, these shifts show up as sharp changes in temperature and gas concentrations. They suggest that once certain conditions are met, feedbacks within the system can accelerate change. For Antarctica, these thresholds are particularly important. The growth and stability of the ice sheet depend on a balance between snowfall, melting, and the flow of ice toward the ocean. Small changes in temperature or ocean conditions can tip that balance, especially at the edges of the ice sheet. The Frozen Archive helps scientists identify past moments when the system approached or crossed such thresholds. By studying what happened then, they can better understand what might happen in the future. The ice also holds more localized stories. In some cores, researchers have found evidence of ancient storms preserved as layers, with unusually high levels of sea salt or dust. These layers suggest periods of stronger winds or more turbulent weather. In others, they have found hints of changes in snowfall patterns, with thicker or thinner annual layers reflecting wetter or drier conditions. All of this information is encoded in subtle variations, often invisible to the naked eye. It takes careful laboratory work, precise instruments, and years of analysis to extract and interpret these signals. There is a certain patience required in this kind of science that feels well matched to the subject. The ice accumulated slowly, it moves slowly, and it gives up its secrets slowly. What makes this record even more remarkable is how fragile it can be. Once an ice core is removed from the cold environment of Antarctica, it must be carefully stored and transported to keep it from melting or changing. The information it contains can be lost if the ice warms or is contaminated. This has led to the creation of specialized facilities around the world where ice cores are kept in deep freeze conditions, sometimes in underground vaults, to preserve them for future research. These stored cores are not just for the scientists who drilled them. They are considered a shared resource available for future generations of researchers who may have new questions or better tools. In a sense, this extends the idea of the ice as an archive. Not only does it preserve the past in its layers, but it is being preserved itself as a record for the future. Beyond the ice sheet, frozen clues exist in other forms as well. Permafrost, permanently frozen ground, can preserve ancient soils, plant remains, and even microorganisms. In parts of Antarctica, especially in the ice-free valleys, these frozen sediments offer another window into the continent's past. Sediment cores taken from the ocean floor around Antarctica also contain valuable records. Layers of mud, sand, and biological material accumulate over time, capturing information about ocean temperatures, ice extent, and marine life. By combining data from ice cores, land-based sediments, and marine records, scientists can build a more complete picture of how Antarctica and the global climate system have evolved together. What emerges from this combined record is a story of connection. The frozen layers in the heart of Antarctica are linked to changes in the atmosphere, the oceans, and the land far beyond the continent itself. A shift in vegetation in the tropics can influence dust levels that end up in Antarctic snow. A change in ocean circulation can alter the chemistry of the air above the ice. This interconnectedness is one of the most powerful lessons of the frozen archive. It shows that no part of the planet operates in isolation. The conditions in one region can leave traces in another thousands of kilometers away. As you think about this, it might be interesting to imagine the ice beneath Antarctica not just as a barrier or a landscape, but as a kind of library. Each layer is a page. Each bubble of air is a sentence. Each grain of dust is a footnote pointing to a distant place or event. Reading that library requires effort and care, but the story it tells is rich and detailed. It speaks of warm worlds and cold ones, of forests and glaciers, of shifts in the chemistry of the air and the movement of the oceans. It also speaks of change, not as a rare or exceptional thing, but as the normal state of the planet. The frozen record shows that Earth's climate has always moved through different phases. What we think of as normal is often just a snapshot in a much longer sequence. At the same time, the record highlights how unusual the present moment is. In certain ways, the recent rapid rise in greenhouse gas levels stands out in the context of the long-term data preserved in the ice. The speed of this change is much faster than most of the natural variations seen in the past. This doesn't make the ice cores a tool for prediction on their own, but it does provide a baseline, a deep context for understanding what kinds of changes the Earth system has experienced before and how it has responded. For Antarctica, the frozen clues locked in time connect its green past to its icy present. They show how the continent moved from forests and rivers to glaciers and ice sheets, step by step through a series of shifts recorded in snow and air and dust. When you look at Antarctica from a distance, whether on a map or in a satellite image, it can feel like a place set apart from the rest of the world. A white mass at the bottom of the globe, surrounded by dark water, seemingly disconnected from the everyday concerns of cities, forests, and farmland. Yet the more scientists have learned about this continent, the clearer it has become that Antarctica is not a distant outlier. It is one of the most important classrooms the planet has. A place where the long story of Earth's climate is written in a way that can still be read, studied, and in many cases understood. To see what Antarctica teaches us, it helps to step back from the details of ice cores, ocean currents, and tectonic plates, and think about the bigger picture. Climate is not just about how warm or cold a place is on a given day. It is about patterns about the way heat, water, air, and energy move around the planet over years, centuries, and millions of years. It is about how these patterns respond to changes. Whether those changes come from deep inside the Earth, from the movement of continents, from the chemistry of the atmosphere, or from the slow rhythm of the planet's orbit around the sun. Antarctica's history touches all of these elements. Its transformation from a green river-carved land to a frozen continent wrapped in ice sheets did not happen because of a single cause. It happened because several different systems shifted at the same time, reinforcing one another in ways that pushed the climate toward a new state. One of the most important lessons from this story is the idea of balance. For long periods, Antarctica existed in a kind of climate balance where forests, rivers, and seasonal snow could all coexist. The continent was cool, especially in winter, but not cold enough to maintain permanent continent-wide ice. Snow fell and melted. Ice formed in high places and disappeared in lower ones. The system had room to move back and forth without tipping into a completely different mode. Over time, that balance changed. Carbon dioxide levels in the atmosphere declined. The continent drifted farther south. Ocean currents reorganized, cutting off a major source of warmth. The amount of sunlight reaching the surface during summer shifted due to changes in the Earth's orbit and tilt. None of these changes on their own would necessarily have been enough to freeze an entire continent. Together they were. This layered cumulative process is one of the clearest messages Antarctica offers about how climate works. It is rarely a single switch being flipped. More often, it is a set of slow-moving controls, each turning a little, sometimes in different directions, until the overall system reaches a point where it behaves differently than it did before. Another lesson comes from the idea of feedback. In climate science, a feedback is a process that either amplifies or dampens a change. Antarctica's ice sheets provide a powerful example of a positive feedback, one that amplifies cooling. As ice spreads, it reflects more sunlight. Reflecting more sunlight means less heat is absorbed by the surface. Less absorbed heat leads to cooler temperatures. Cooler temperatures make it easier for more ice to form. This loop can continue reinforcing itself. This doesn't mean the system is unstoppable. Other feedbacks can work in the opposite direction. For example, as ice retreats, darker land or water is exposed, which absorbs more sunlight and can promote warming. What Antarctica shows is how strong these feedbacks can be, especially when they involve something as widespread as a continent-sized ice sheet. Once ice became the dominant feature of the landscape, it didn't just respond to the climate. It became one of the main drivers of the climate in that region and beyond. The continent also highlights the role of thresholds. For long stretches of time, Antarctica hovered near the boundary between an ice-free or partially ice-covered state and a fully glaciated one. The difference between those states depended on relatively small changes in temperature, snowfall, and ocean conditions. When the system crossed a certain threshold, ice began to grow in a way that was much harder to reverse. The feedbacks kicked in, the reflective surface spread. The ocean circulation adjusted. The land sank under the weight of the ice, making it colder at the surface. This idea of thresholds is important because it suggests that climate systems can behave in nonlinear ways. change doesn't always happen gradually and smoothly. Sometimes a slow buildup of pressure or influence leads to a relatively rapid shift from one state to another. The geological record in Antarctica captures moments like this. The transition around 34 million years ago, when ice sheets expanded rapidly, stands out as a point where the climate system moved into a new mode. Before that, ice was regional and temporary. After that, it became continental and persistent. Another key lesson from Antarctica is the importance of the oceans in regulating climate. It is easy to focus on air temperatures and atmospheric gases because they are the most obvious parts of the system for people living on land. But the oceans store far more heat than the atmosphere does. They move that heat around the globe through complex patterns of currents. The formation of the Antarctic circumpolar current changed how heat was distributed between the hemispheres. By isolating Antarctica from warmer waters, it helped lock the continent into a cold state. At the same time, it linked the major ocean basins, influencing global circulation patterns. This shows how a change in one part of the ocean system can ripple outward, affecting climates far away. The cold, dense water formed near Antarctica today sinks and spreads northward, influencing conditions in the Atlantic, Pacific, and Indian Oceans. In this way, Antarctica acts as one of the engines of the global climate system. Its state influences not just the southern hemisphere, but the entire planet. The continent also offers a long-term perspective on greenhouse gases. The air bubbles trapped in its ice cores provide a direct record of how the composition of the atmosphere has changed over hundreds of thousands of years. When scientists compare this record to temperature estimates from the same ice, they see a clear relationship. Higher levels of carbon dioxide and methane are associated with warmer periods. Lower levels align with colder glacial periods. This doesn't mean that greenhouse gases are the only factor influencing climate. Orbital cycles, volcanic activity, and changes in land and ocean configurations all play roles. But the ice core record shows that greenhouse gases are a powerful amplifier of whatever trend is underway. In Antarctica's past, relatively small changes in sunlight due to orbital cycles could be strengthened by changes in atmospheric composition, leading to much larger shifts in temperature and ice extent. This insight is especially valuable because it comes from direct physical evidence rather than models or theory alone. The ice itself holds samples of ancient air, making the link between gases and climate something that can be measured, not just inferred. Another lesson lies in the way different parts of the Earth system interact. Antarctica's story is not just about ice and temperature. It is about how vegetation, oceans, atmosphere, and landforms influence one another. When Antarctica was green, forests and wetlands would have played a role in the carbon cycle, taking in carbon dioxide from the air and storing it in plant material and soils. Rivers would have carried organic matter to the sea, where some of it would have been buried in sediments. As the continent froze, that biological activity declined. The carbon cycle in the region changed. The land surface became less active in terms of absorbing and releasing gases. This kind of shift can influence the broader climate system, especially when it happens over large areas. Antarctica shows how changes in ecosystems and climate can be linked in both directions, with each influencing the other. The continent also teaches us about time scales. Many of the processes that shaped Antarctica operate so slowly that they are almost invisible on a human time scale. The drift of tectonic plates, the buildup of ice sheets, the slow changes in the Earth's orbit. At the same time, the record shows that some changes once triggered can unfold relatively quickly in geological terms. Ice sheets can expand or retreat over thousands of years, which is fast compared to the millions of years it took for the continents to move into their current positions. This range of time scales is an important part of understanding climate. Some changes are background conditions, setting the stage for what is possible. Others are more immediate, determining what actually happens within that stage. Antarctica's history illustrates how these layers of time interact. The long-term movement of the continent placed it in a position where it was vulnerable to cooling. The medium-term changes in ocean circulation and atmospheric composition pushed it closer to a tipping point. The shorter-term orbital cycles helped determine when that tipping point was crossed. Another insight comes from the idea of resilience and limits. For a long time, life on Antarctica adapted to changing conditions. Forests shifted, animals migrated or adjusted their behavior. Ecosystems reorganized. But there came a point where the changes outpaced the ability of many species to cope. The expansion of ice reduced available habitat to such an extent that most land-based ecosystems could no longer survive on the continent. This highlights a general principle in ecology and climate science. Systems can absorb a certain amount of change. They can bend without breaking. But beyond certain limits, they can reorganize in ways that are difficult or impossible to reverse, at least on the same time scale. In Antarctica, the shift from a land-based ecosystem to an ice-dominated one represents such a reorganization. Once the ice sheet became established, the conditions that supported forests and rivers were no longer present. The continent's role as a climate archive also teaches us about the value of records. Without the ice cores, the buried landscapes, and the fossil evidence, much of this story would remain hidden. The ice sheet preserves not just the memory of Antarctica's own past, but also signals from around the world. Dust from distant deserts, ash from far-off volcanoes, traces of changes in ocean biology. All of these end up in the frozen layers, creating a global record stored in one place. This makes Antarctica a kind of reference point for understanding Earth's climate history. By comparing its record with data from other regions, scientists can see which changes were local and which were global, which were driven by regional processes and which by planetary scale shifts. There is also a lesson here about perspective. It is easy to think of climate in terms of what we experience directly, the weather outside our window, the seasons in our region. Antarctica's story encourages a broader view, one that spans continents and oceans, years and millennia. It shows that what happens in one place can be influenced by events far away, and that the effects of local changes can propagate across the globe. In practical terms, this means that understanding climate change today requires looking at the whole system, not just one part of it. Changes in the Arctic, for example, can influence weather patterns in the middle latitudes. Changes in the Southern Ocean can affect the uptake of carbon dioxide from the atmosphere. Antarctica sits at a key position in this system. Its ice sheet stores an enormous amount of frozen water. If significant portions of that ice were to melt and flow into the ocean, global sea levels would rise, affecting coastlines around the world. Its surrounding ocean plays a major role in absorbing heat and carbon dioxide from the atmosphere. Changes in that ocean could influence how much warming the planet experiences. The continent's past shows that its state can change given the right conditions. It also shows that when it does change, the effects can be far-reaching. Another important teaching from Antarctica is the role of uncertainty and discovery. Even with decades of research, there is still much that scientists do not fully understand about how the ice sheet behaves, how the ocean interacts with it, and how these processes might respond to future changes. The hidden landscape beneath the ice, for example, is still being mapped. The details of subglacial water systems, geothermal heat flow, and the mechanical properties of ice are active areas of research. This ongoing work is a reminder that science is not a finished product. It is a process of asking questions, testing ideas, and refining understanding as new information becomes available. Antarctica, because of its remoteness and extreme conditions, makes this especially clear. Each field season, each drilling project, each new set of measurements can add something unexpected to the picture. There is also a broader, almost philosophical lesson in the way the continent story unfolds. It highlights the deep time of the planet. The idea that the world we inhabit is just one moment in a long sequence of different states. The green Antarctica of the past and the frozen Antarctica of the present are both part of the same continuum. Neither is more natural than the other. They are simply different expressions of the Earth system under different conditions. This perspective can change how we think about stability and change. It suggests that change is not an anomaly, but a constant. What varies is the pace and the direction. At the same time, it underscores the significance of rapid change. When shifts happen faster than the systems involved can adapt, the consequences can be profound. Antarctica's transition from green to frozen took millions of years. The changes happening in the climate system today are unfolding over decades and centuries. The comparison is not exact, but it highlights the difference in time scales and the potential challenges for ecosystems and human societies. As you reflect on what Antarctica teaches us, it might be helpful to think of the continent as both a mirror and a window. It reflects the broader workings of the Earth system, showing how land, sea, air, and life interact. It also provides a window into the past, offering a long-term view of how those interactions have played out under different conditions. This combination makes it a powerful source of insight, not just for scientists, but for anyone interested in how the planet functions. The lessons are not simple or neatly packaged. They involve complexity, feedbacks, thresholds, and deep time. They challenge the idea that the world is static or predictable in a straightforward way. Instead, they point to a system that is dynamic, interconnected, and responsive to a wide range of influences. Imagine for a moment that the ice which now defines Antarctica begins to lift, not in a rush, not in a sudden collapse, but slowly, steadily, like a curtain being drawn back over the course of many lifetimes. The wind still blows. The sun still circles low in the sky during summer and disappears for long stretches in winter. But the white surface that once reflected almost everything gives way piece by piece to darker shapes and textures underneath. What would come into view is not an empty, featureless plain, but a continent with a shape and character that has been hidden for millions of years. The first thing you might notice is how varied the land actually is. From above, Antarctica often looks smooth and uniform, a broad expanse of white stretching from one horizon to the other. Beneath that surface, however, lies a terrain as complex as any on Earth. There are mountain ranges, some sharp and jagged, others worn and rounded by ancient erosion. There are broad lowlands that dip far below what we think of as sea level. There are deep valleys that twist and branch, tracing the paths of rivers that once flowed across the land. One of the most striking features that would emerge is the trans-Antarctic mountains. These mountains already peek through the ice in places, forming a long spine that divides East and West Antarctica. Without the ice, their full extent would become clear. They stretch for thousands of km, a chain of peaks, ridges, and plateaus that rivals some of the major mountain systems on other continents. In some areas, these mountains rise steeply from the surrounding land, forming dramatic cliffs and high valleys. In others, they blend more gently into rolling highlands. Their rocks tell stories of ancient collisions between tectonic plates, of volcanic activity, and of long periods of erosion by wind and water. To the east of this range lies a vast region known as East Antarctica, which beneath the ice is a high, stable plateau. Much of this area sits hundreds of meters above sea level, even after accounting for the weight of the ice that has pressed it down over time. This high ground would likely form the backbone of any ice-free version of the continent, with broad, open landscapes stretching toward the horizon. In contrast, West Antarctica is very different. Beneath the ice there, Much of the land lies far below sea level. This region is more like a series of deep basins and troughs, separated by ridges and mountain ranges. If the ice were gone and the ocean were allowed to flow in, large parts of West Antarctica would likely become an archipelago, a scattering of islands separated by shallow seas. This difference between East and West is one of the most important features of the hidden continent. It reflects a complex geological history, with different parts of Antarctica forming and evolving in different ways. As the ice retreats from these low-lying basins, the ocean would begin to claim them. Seawater would flood in through existing coastal openings, filling valleys and depressions. Over time, new coastlines would form, carving known shapes into what was once an unbroken mass of ice. The result would be a continent with a far more intricate shoreline than the one we see today. Instead of a smooth, icy edge, there would be bays, inlets, peninsulas, and islands. The meeting point between land and sea would stretch for thousands of kilometers, creating a wide range of coastal environments. Along these new coasts, the interaction between land and ocean would shape the climate and ecosystems in powerful ways. Coastal areas tend to be milder than interior regions, thanks to the moderating influence of the sea. Even in high latitudes, this effect can make a significant difference. In a hypothetical ice-free Antarctica, the coasts might support environments similar to those found in the far southern reaches of South America or the sub-Antarctic islands today. Cold, windy, and seasonal, but not locked in permanent ice. Moving inland from the coast, the land would begin to rise in many places, especially in East Antarctica. Broad plateaus and high plains would dominate the interior. These areas would experience colder temperatures and stronger winds, particularly during the long winter months when the sun remains below the horizon. Without the ice sheet, the atmosphere above these highlands would behave differently. The smooth, reflective surface that currently cools the air and stabilizes certain wind patterns would be gone. Darker ground would absorb more sunlight during summer, warming the surface and the air above it. This would likely lead to more active weather systems. Air would rise over warmer land, creating areas of lower pressure that draw in winds from surrounding regions. Storms could form more easily, especially near the coasts, where temperature differences between land and sea would be more pronounced. Rain and snow would fall in patterns shaped by the terrain. Mountains would force moist air to rise, cooling it and causing precipitation on their windward sides. The leeward sides would lie in rain shadows, drier and more exposed. Over time, rivers would once again carve their way across the landscape. Some would follow ancient valleys that had been buried under ice. Others would find new paths, responding to the changed shape of the land and the presence of newly formed seas and lakes. These rivers would play a central role in shaping the emerging ecosystems. They would carry nutrients from the interior to the coasts, supporting plant growth along their banks and in the coastal waters where they meet the sea. Lakes would form in natural basins, especially in areas where the land had been depressed by the weight of the former ice sheet. As the crust slowly rebounded, a process that can take thousands of years, these basins would change shape, sometimes draining, sometimes filling, creating a dynamic network of freshwater environments. In these imagined landscapes, life would begin to find footholds. The exact nature of that life would depend on many factors, including how quickly the ice retreated, what species were able to reach the continent, and how the climate evolved over time. Plants would likely be among the first to establish themselves, starting with hardy species that can tolerate cold, wind, and poor soils. Mosses, lichens, and grasses might spread across sheltered areas and along river banks. Over time, as soils developed and conditions stabilized, shrubs and eventually trees could take root in the milder regions. The types of trees that might grow would likely resemble those found in other cold, temperate environments in the southern hemisphere. Species related to southern beaches and conifers might dominate, forming open forests rather than dense tropical jungles. Animals would follow the plants. Insects and other small invertebrates would arrive first, carried by winds or birds or transported on floating debris. Birds themselves would be among the earliest vertebrates to establish populations drawn by the coastal environments and the availability of food in the sea. Over longer periods, mammals could arrive either by crossing land bridges, if any, formed, or by traveling over ice or water. The exact pathways would depend on the configuration of the continents and the climate at the time. The marine environment around an ice-free Antarctica would also be very different. Without the massive ice shelves and the constant formation of sea ice, the interaction between the ocean and the atmosphere would change. The surface waters would likely be warmer, especially in summer, and more exposed to wind and waves. This could increase mixing between surface and deep waters, bringing nutrients up from below and supporting productive marine ecosystems. Coastal seas might become rich fishing grounds similar to those found in other parts of the world, where cold, nutrient-rich waters meet the light of the sun. The loss of the ice sheet would also have global effects. The water currently locked up in Antarctic ice represents a huge volume. If it were all to melt and flow into the ocean, global sea levels would rise by tens of meters, reshaping coastlines around the world. Cities and low-lying regions far from Antarctica would be affected, illustrating once again how connected the planet's systems are. A change at the bottom of the world would not stay there. It would ripple outward, touching nearly every coastline. Beyond the physical changes, an ice-free Antarctica would offer an unprecedented window into the planet's past. The land that emerged would expose rock layers and fossil beds that have been sealed away for millions of years. Geologists would be able to walk across surfaces that last saw sunlight in a world without humans. Paleontologists could search for fossils in places that have been inaccessible since the time of dinosaurs and early mammals. These discoveries could fill in gaps in our understanding of how life evolved in the southern hemisphere, how continents moved and collided, and how climate shifts influenced the distribution of species. The exposed terrain would also reveal more about the deep structure of the continent. Fault lines, volcanic features, and ancient mountain routes would become visible, offering clues about the forces that shaped Antarctica long before it became a land of ice. In some areas, geothermal activity might play a noticeable role. Even today, there are regions beneath the ice where heat from the Earth's interior is relatively high. Without the insulating layer of ice, these areas might support warmer ground, perhaps even small zones of steaming vents or hot springs. Such features would create localized pockets of milder conditions, which could serve as refuges for life in an otherwise cold and challenging environment. The atmosphere above an ice-free Antarctica would also behave differently. The current ice sheet plays a role in shaping global wind patterns, especially the strong westerly winds that circle the southern hemisphere. Without the cold, high surface of the ice, the temperature gradient between the continent and the surrounding ocean would change. This could alter the strength and position of these winds, with effects that extend into the mid-latitudes. Weather patterns in parts of the southern hemisphere might shift, influencing rainfall and temperature in regions far from the continent itself. It is important to remember that this imagined scenario does not represent a simple return to the Antarctica of the distant past. The world today is different in many ways. The positions of the continents have changed. The composition of the atmosphere is different. The ocean basins have a different shape. An ice-free Antarctica in the future would not be a perfect mirror of the green Antarctica of the past. It would be a new state shaped by both ancient geology and modern conditions. There is also the question of time scale. The retreat of a continent-sized ice sheet would not happen in a single lifetime or even over a few centuries. It would likely take thousands of years, even under sustained warming. During that time, the land would go through many phases. Some areas might become ice-free, while others remain covered. Lakes might form and drain. Coastlines would shift as the crust rebounds and sea levels change. Life would adapt to these changing conditions, moving into newly available habitats and retreating from others. This dynamic process highlights another lesson from Antarctica's history. Landscapes are not static. They're always in the process of becoming something else. The hidden valleys beneath the ice today are evidence of that. They show that the land once looked very different, shaped by water and vegetation rather than ice. If the ice were gone, the continent would not simply reveal a frozen ancient world. It would begin a new chapter, one in which old features interact with new conditions to create a landscape that has never existed before. There is a certain humility that comes with considering this. It reminds us that the world we see around us, whether it is a city, a forest, or a frozen continent, is just one version of a place that has taken many forms over time and will likely take many more in the future. Antarctica, in its present state, feels like an end point, a place where the story of green landscapes and flowing rivers has come to a stop, replaced by ice and wind. But in a longer view, it is not an end point at all. It is a moment in an ongoing process. The land beneath the ice is still there, shaped by ancient rivers and forests, bearing the marks of tectonic forces and climate shifts. The ice above it is still moving, still responding to changes in temperature, snowfall, and ocean conditions. If that ice were to retreat, the continent would not simply go back in time. It would move forward into a new state, carrying its deep history with it in the shape of mountains, valleys, and basins that would once again meet the sky. As you sit with this imagined landscape, it might be interesting to think about how much of the world you know is similarly shaped by hidden histories. The ground beneath your feet may have once been a seafloor, a riverbed, or a forest long gone. Antarctica makes this idea especially vivid because the contrast between what we see and what lies beneath is so extreme. In that contrast, there is a quiet invitation to look at the planet not just as it is, but as it has been and as it might become. The ice, for all its dominance, is just one layer in a much longer story. The southernmost continent remains one of the clearest, most powerful places to see how deeply the past, the present, and the future are woven together in the fabric of the Earth. There is a temptation when looking at a place like Antarctica to think of it as finished, settled into its final form, a frozen continent at the end of the world, locked in ice, far removed from the rhythms of everyday life. Yet in reality, almost nothing about it is truly still. Beneath the ice, the land continues to shift. Above it, the atmosphere and the oceans continue to move heat, moisture, and energy around the globe. And within the ice itself, slow, persistent motion carries frozen water from the high interior toward the sea. To think about the future of Antarctica is to think about a system that is always in motion, even when that motion is measured in millimeters per year, or in changes that take centuries to become obvious. At the deepest level, the continent is still riding on a tectonic plate that drifts across the surface of the planet. This movement is so slow that it feels almost abstract, but it is real. Over millions of years, it has carried Antarctica from a position connected to other southern continents into its current place near the South Pole. That journey has not ended. The plate beneath Antarctica continues to respond to forces in the Earth's mantle. It may rotate slightly. It may shift northward or eastward by small amounts. These changes are tiny on a human time scale, but over geological time, they can alter the continent's position relative to the sun and the oceans. While these deep movements at the long-term stage, the more immediate changes happening now and in the coming centuries are driven by the interaction between the ice, the ocean, and the atmosphere. One of the most visible signs of motion is the ice itself. The Antarctic ice sheet is not a static block of frozen water. It behaves more like a very slow-moving fluid. Snow falls in the interior, building up layer by layer. The weight of that accumulation pushes the ice outward toward lower elevations and eventually toward the coast. This flow creates a network of glaciers that act like highways, carrying ice from the heart of the continent to the sea. Some of these glaciers are hundreds of km long and move several meters per year. Others are slower, creeping along at a pace that is almost imperceptible without precise measurements. Where these glaciers reach the coast, they often form ice shelves, floating extensions that spread out over the ocean. These shelves can be tens to hundreds of meters thick and can cover areas larger than some countries. The stability of these shelves is one of the key factors in determining how quickly the ice sheet loses mass. When shelves are intact, they act as a kind of brake, slowing the flow of glaciers behind them. When they thin or break apart, the glaciers can accelerate, sending more ice into the ocean. This interaction between ice and ocean is one of the most dynamic parts of the Antarctic system. Even small changes in ocean temperature can have a significant effect on how much melting occurs beneath the shelves. In some parts of West Antarctica, relatively warm water from the deep ocean can make its way onto the continental shelf and flow beneath the ice shelves. This water may be only a few degrees above freezing, but that is enough to melt ice from below. As the shelves thin, cracks can form. Large sections can break off, creating icebergs that drift away into the Southern Ocean. The loss of a shelf can change the balance of forces acting on the glaciers behind it, allowing them to speed up. This kind of change has already been observed in several regions. It serves as a reminder that the ice sheet responds to its environment, sometimes in ways that are not immediately obvious, but can become significant over time. The atmosphere plays its role as well. Winds around Antarctica are among the strongest and most persistent on Earth. They drive the circumpolar current in the ocean and influence how heat and moisture are distributed around the continent. Changes in global climate patterns can alter the strength and position of these winds. For example, shifts in the temperature difference between the equator and the poles can affect how the jet streams behave, which in turn can influence weather systems in the southern hemisphere. When wind patterns change, they can affect how much warm air reaches the Antarctic coast and how much sea ice forms in the surrounding ocean. Sea ice, like land ice, reflects sunlight and insulates the ocean beneath it. Its extent and thickness can influence how much heat the ocean absorbs and releases. The relationship between sea ice and the ice sheet is another example of feedback. More sea ice can help keep coastal waters colder, reducing melting of ice shelves. Less sea ice can allow more heat from the ocean to reach the shelves, increasing melting. These interactions create a complex moving system where changes in one part can ripple through the others. There is also movement happening beneath the ice in the land itself. The weight of the ice sheet presses down on the crust, causing it to sink. This process, known as isostatic adjustment, is reversible. When ice thins or retreats, the land can begin to rise again. This rebound can take thousands of years, but it can have important effects on the shape of the coastline and the depth of the ocean near the continent. In some regions, this rising land could make it harder for the ocean to reach the base of glaciers, potentially slowing melting. In others, changes in the shape of the seabed could alter how currents flow, influencing where warm water can access the ice. This adds another layer of motion to the system. The ice affects the land affects the ocean affects the ice. Beyond these physical processes, there is the broader context of how the planet's climate is evolving. The concentration of greenhouse gases in the atmosphere influences how much heat the Earth retains. This in turn affects temperatures in the air and the ocean. Antarctica's past shows that the ice sheet is sensitive to long-term changes in these conditions. When global temperatures were higher and atmospheric carbon dioxide levels were elevated, the continent was largely ice-free. When temperatures dropped and carbon dioxide levels declined, ice expanded. The present situation is different in many ways, but the basic relationships still apply. Warmer air can hold more moisture, which can lead to increased snowfall in some parts of Antarctica. At the same time, warmer oceans can increase melting at the edges of the ice sheet. This creates a complex picture. In some regions, the ice sheet might gain mass. In others, it might lose mass. The overall balance depends on how these processes play out across the entire continent. Scientists use a combination of satellite observations, field measurements, and computer models to try to understand and project these changes. Satellites can track the movement of ice, measure changes in ice thickness, and monitor the extent of sea ice and ice shelves. On the ground, researchers drill ice cores, install GPS stations to measure land movement, and deploy instruments to study ocean conditions near the ice front. These data provide the details needed to test and refine models of how the system works. The models themselves are tools for exploring possible futures rather than making precise predictions. They can simulate how the ice sheet might respond to different scenarios, such as changes in greenhouse gas concentrations, ocean temperatures, or snowfall patterns. What these simulations often show is that parts of the Antarctic ice sheet, particularly in West Antarctica, may be more vulnerable to sustained warming than others. This region's low-lying basin-shaped terrain makes it more susceptible to a process known as marine ice sheet instability. In simple terms, if the grounding line, the point where the ice sheet rests on the land and begins to float, retreats into deeper water, the ice can become more unstable and retreat more rapidly. This can create a self-reinforcing cycle of ice loss. East Antarctica, with its higher, more stable bedrock, is generally thought to be more resistant to rapid change. But even there, certain coastal regions may be sensitive to warming oceans. These differences highlight another aspect of motion in the future of the continent. Change is not likely to be uniform. Some areas may remain relatively stable for a long time. Others may undergo more noticeable shifts. The implications of these changes extend far beyond Antarctica itself. The ice sheet contains enough frozen water to raise global sea levels by many tens of meters. If it were to melt completely, even a small percentage of that total would have significant effects on coastal regions around the world. Sea level rise does not happen all at once. It unfolds over decades and centuries, but it can reshape coastlines, increase the frequency of flooding, and affect ecosystems and human settlements. This means that the future of a continent still in motion is tied to the future of places far from the polar regions. A glacier speeding up in West Antarctica can eventually influence a shoreline in the tropics, or a river delta thousands of kilometers away. There is also a future for Antarctica that goes beyond physical changes. The continent has become a focus of international cooperation through agreements that emphasize scientific research and environmental protection. This framework has helped keep Antarctica free from permanent human settlement, large-scale resource extraction, and military activity. It has turned the continent into a kind of shared space, dedicated to understanding the planet rather than exploiting it. How this arrangement evolves over time will be part of the human side of Antarctica's future. As technology advances and global pressures change, there will likely be ongoing discussions about how the continent should be used and protected. Scientific research is likely to continue to expand. New methods for exploring beneath the ice, such as advanced radar and autonomous underwater vehicles, are already revealing more about the hidden landscape and the behavior of the ice and ocean. These tools may uncover new subglacial lakes, map previously unknown mountain ranges, and provide more detailed records of past climate conditions. Each discovery adds to the picture of how Antarctica has changed and how it might change again. The future also holds questions about life in and around the continent. Marine ecosystems in the Southern Ocean are closely tied to the presence of sea ice and the timing of seasonal changes. Krill, for example, a small shrimp-like creature, forms the base of much of the Antarctic food web. Its life cycle is linked to sea ice, which provides both food and shelter for its larvae. Changes in sea ice patterns could affect krill populations, which in turn could influence penguins, seals, whales, and other species that depend on them. On land, life is limited, but even small shifts in temperature and moisture can affect the distribution of mosses, lichens, and microbial communities. These organisms may expand into new areas or retreat from others as conditions change. This biological motion, subtle and often overlooked, is another layer of the continent's ongoing transformation. There is also the long view, the perspective that looks beyond the next few centuries or even the next few millennia. Over millions of years, the tectonic movement of the continent will continue. The configuration of the continents and oceans will change. New supercontinents may form. In such a distant future, Antarctica may no longer sit at the South Pole. It may drift into lower latitudes, receiving more direct sunlight and experiencing a very different climate. If that were to happen, the ice sheet could eventually disappear, revealing the land beneath and allowing new ecosystems to develop. The green landscapes of the past could in some form return, shaped by a world that has changed in countless other ways. This perspective emphasizes that the frozen state of Antarctica is not a permanent feature of the planet. It is a phase in a much longer cycle of change. At the same time, the near-term future is shaped by decisions and actions taken by people around the world. The way energy is produced, how land is used, and how emissions are managed all influence the conditions that affect the global climate system. Antarctica's ice sheet responds to those conditions, not directly, but through the interconnected web of atmosphere and ocean. This connection between human activity and a remote, seemingly untouched continent can feel abstract. Yet the physical links are real. Changes in the chemistry of the air over cities and forests eventually influence the temperature of the ocean currents that reach the Antarctic coast. The future of the continent, in that sense, is tied to the future of the broader Earth system. As you think about a continent still in motion, it can be helpful to picture the different layers of movement happening at once. There is the deep, slow drift of tectonic plates. There is the steady flow of ice from the interior to the sea. There is the constant circulation of the ocean and the shifting patterns of the atmosphere. There is also the movement of information and understanding as scientists gather data, refine models, and share insights about how the system works. These layers interact, sometimes in predictable ways, sometimes in ways that surprise. The story of Antarctica's future is not written yet. It is being shaped by processes that began millions of years ago and by influences that are unfolding now. What remains consistent is the idea that the continent is part of a dynamic planet. It is not a static backdrop, but an active participant in the Earth's ongoing evolution. As the ice continues to flow, the winds continue to circle, and the oceans continue to move heat around the globe. Antarctica remains a place where deep time and present day change intersect. In that intersection, the frozen past, the shifting present, and the uncertain future are all layered together, much like the ice itself, forming a complex, evolving record of a world that is always in one way or another in motion. As the long arc of this story begins to settle into something quieter, it helps to return not to a diagram or a timeline, but to a simple image, a wide horizon. A low sun tracing a slow circle through the sky. Wind moving across a surface that looks at first glance like nothing more than white and blue. Antarctica in its present form can feel like the end of a journey. A place where the world runs out of familiar shapes and sounds. Yet when you carry everything we've explored with you into that scene, the stillness begins to feel different. The ice is no longer just ice. It becomes a surface that rests on forests that once stood, rivers that once ran, mountains that rose and wore down, and air that once held the breath of creatures moving through a very different world. Standing in this imagined place, you're not really at the end of anything. You're standing in the middle of a story that has been unfolding for hundreds of millions of years and will continue long after the present moment has passed. The land beneath the ice is still there. That is one of the quiet truths that can change how you see this continent. Beneath kilometers of frozen water, the ground holds its shape, its scars, and its memories. Valleys carved by ancient rivers still curve through the bedrock. Mountain ridges still push upward, even if their peaks only appear in rare rocky outcrops. Basins still dip far below sea level, waiting under the weight of ice. This hidden world is not a relic in the sense of being finished. It is a foundation, something that continues to influence how the ice moves, where water flows beneath the surface, and how the continent responds to changes in temperature and ocean conditions. Above it, the ice is not a static cover. It is a slow-flowing presence, always shifting, always responding to gravity, snowfall, and the pull of the sea. Every year, a new layer settles on top. Every year, a little bit of ice reaches the coast and becomes part of the ocean. In this way, Antarctica is always giving something back to the wider world. It contributes cold, dense water to the deep ocean currents that travel far beyond the southern hemisphere. It reflects sunlight back into space, influencing how much heat the planet absorbs. It stores a vast amount of frozen water, shaping the level of the seas that touch every coastline on Earth. These roles are not dramatic in the way we often imagine change. They are quiet, steady, and persistent. They happen whether or not anyone is paying attention. There is something about that quiet persistence that invites a different kind of reflection. In many places, the marks of human activity are obvious. Cities rise, roads cut across landscapes, and lights glow at night. In Antarctica, those marks are minimal. The continent remains for the most part a place shaped by wind, water, rock, and ice rather than by human hands. This does not mean it is untouched by human influence. The atmosphere that drifts over the ice carries gases and particles from all over the world. The ocean currents that brush against the ice shelves carry heat that has been redistributed by global climate patterns. The connection is indirect, but it is real. A factory, a forest, a car, a power plant, all can play a role, however small, in the conditions that reach the edge of the Antarctic ice. That link can feel abstract, but it becomes more tangible when you think about how the planet works as a whole. The air does not belong to one place. The oceans do not stop at national borders. Heat, moisture, and energy move around the globe in ways that tie distant regions together. Antarctica is one of the places where those global movements become especially visible. The circumpolar winds circle the continent, connecting the Atlantic, Pacific, and Indian Oceans. The deep water formed near the ice sinks and spreads, becoming part of a planetary-scale circulation system. From this perspective, the frozen South is not isolated. It is a hub, a point where many of the planet's major systems intersect. There is a certain humility that comes with recognizing that. It suggests that no place, no matter how remote, exists on its own. Every part of the Earth is part of a larger pattern. That idea can shift how you think about the earlier chapters of the story. The green Antarctica of the past was not just a local curiosity. It was part of a global world connected to other continents through shared ecosystems, ocean currents, and atmospheric patterns. The freezing of Antarctica was not just a local event either. It reshaped ocean circulation, influenced global climate, and helped set the stage for the ice ages that would later affect much of the northern hemisphere. This back and forth between local and global, between a single place and the whole planet, runs through everything we've explored. It is one of the quiet themes that emerges when you step back and look at the long view. Another theme is time, not in the sense of hours or days, but in the sense of deep time. The kind of time that is measured in millions of years, rather than in calendars. Antarctica's story unfolds at that scale. The drifting of continents, the opening and closing of ocean passages, the rise and fall of greenhouse gas levels, the advance and retreat of ice sheets. These processes move slowly, often too slowly to notice within a single lifetime. Yet their effects are anything but small. They determine whether a continent is covered in forests or buried under ice. They shape the level of the oceans and the patterns of the winds. They influence where life can thrive and where it cannot. Thinking in this way can make the present moment feel both significant and fleeting. Significant because it is part of this long sequence. One link in a chain that stretches far into the past and the future. Fleeting because in the context of millions of years, even centuries pass quickly. There is also something grounding about this perspective. It places human history within a much larger frame. It reminds us that the world we experience is one version of a planet that has taken many forms and will take many more. The ice beneath Antarctica's sky today is not the first major transformation this land has seen, and it will not be the last. If you imagine standing there in the cold air with the wind moving across the surface, you can almost sense the layers of time beneath your feet. Not in a literal way, of course, but in the awareness that what you see is only the topmost layer for much deeper story. That awareness can make even simple details feel different. A crack in the ice becomes not just a break in a frozen surface, but a reminder of movement and pressure. A rocky outcrop becomes a piece of a mountain range that once stood in a very different climate. A patch of snow becomes part of a record that might one day be drilled and studied as a snapshot of the atmosphere from a specific year in the distant past. There is also a quiet presence of life, even in this extreme environment. Microorganisms in the snow and ice, mosses and lichens clinging to sheltered rocks along the coast. Birds and marine animals moving through the surrounding seas. These forms of life are not echoes of the ancient forests and dinosaurs we talked about earlier, but they are part of the same long lineage of living things responding to the conditions of their world. Their presence is a reminder that life is persistent, adaptable, and often found in places where it seems least likely to thrive. At the same time, the absence of large, complex ecosystems on land highlights how much the environment has changed. It underscores the scale of the transformation that turned a green continent into a frozen one. This contrast can invite a different kind of curiosity, not just about what was, but about what might be possible under different conditions. If the ice were to retreat, what would the land look like? What kinds of ecosystems would emerge? How would the climate and the oceans respond? These questions are not just thought experiments. They connect to real discussions about the future of the planet and the choices being made in the present. Yet, even without projecting forward, there is value in simply sitting with the present form of Antarctica and recognizing it as a moment in a much longer sequence. There is a quiet beauty in that idea. The notion that the ice, the wind, and the sky are part of a story that has no clear beginning or end, only transitions from one state to another. This kind of reflection does not require a conclusion in the usual sense. It does not need a final answer or a neat summary. It is more about holding a set of ideas together and letting them settle. The green continent of the past, the frozen continent of the present, the shifting continent of the future. All three exist at once in the sense that they are connected by the same land, the same planet, the same underlying processes. You might notice, as you think about this, that the idea of an end of the world takes on a different meaning. Antarctica is often described that way because of its position on the globe and its harsh conditions. But in another sense, it is not an end at all. It is a place where many of the planet's stories meet. It is where deep time and present time intersect. where the atmosphere, the ocean, the land, and the ice all interact in ways that shape the global system. That intersection makes it a powerful place for reflection. Even if you never set foot there in everyday life, it is easy to focus on what is close at hand. The weather outside, the tasks of the day, the immediate concerns that fill up attention. Thinking about a place like Antarctica and about the long story it holds can widen that focus. It can create a sense of scale that stretches beyond the usual boundaries of time and space. This does not have to be overwhelming. It can be grounding, a reminder that the world is larger, older, and more interconnected than it often appears. There is also something calming about the pace of the processes we've talked about. Tectonic plates moving a few centimeters a year, ice flowing a few meters a year, orbital cycles unfolding over tens of thousands of years. These are rhythms that operate far outside the speed of modern life. They suggest a different tempo, one where change happens but not in a rush. That does not mean that everything is slow or gentle. The consequences of these slow processes can be dramatic. Continents collide. Ice sheets grow or shrink. Sea levels rise and fall. But the way those consequences unfold is tied to a long, steady movement rather than to sudden, isolated events. Holding that in mind can change how you think about change itself. It becomes less about abrupt endings and more about transitions, about one state gradually giving way to another. Antarctica's transformation from green to frozen was not a single moment. It was a long passage from one set of conditions to another, shaped by many overlapping influences. In the same way, whatever comes next for the continent will likely be another passage, another phase in a story that continues. As this reflection settles, it can be helpful to return once more to a simple, quiet image. The sun low on the horizon, the light spreading across the ice, the wind moving across a surface that holds both the weight of the present and the memory of the past. In that image, there is no need for a final statement. The scene does not demand a conclusion. It simply exists, open to interpretation and thought. The land beneath the ice continues to hold its shape. The ice above it continues to move. The air and the ocean continue to carry heat and energy around the globe. The story continues whether it is being told or not. And in that ongoing movement, there is room for curiosity, for attention, and for the simple act of noticing that even in the coldest, quietest places on Earth, there is a deep living connection to the rest of the world, not an ending, but a pause, a moment to sit with the idea that the planet is always becoming something else, and that every place, no matter how distant or still it may seem, is part of that larger unfolding motion.